Hi, at the time of recording this video, it's 2023 and ChatGPT is taking off. I'm really excited to see what it will do in the future. But what I asked it to do recently is to give me a synopsis of what the Matrix is, as if the program was Morpheus. If you haven't seen the Matrix, it's a great film from the 90s. It's all about an AI that enslaves humanity. What I think is interesting is, well, this is an AI writing about the video, a movie that is about AI. So anyway, have a read and see what you think, and marvel at the intelligence of this computer program. Hi, I'm Michael Palmer, and welcome to the chapter on matrices. This is a new chapter, so let's dive in and have a look at what we've got to learn. You probably remember some stuff about matrices from last year. Today we're going to go over the order of a matrix and some types of matrices to jog your memory. All right, so we won't be talking about the film The Matrix for 10 lessons in a row. We will be talking about matrices, or a matrix is the singular term. Here is a matrix, and you've seen them before last year, I think. So let's go through some things about matrices. What do we know about them? So a matrix is often labeled with a capital letter. So you can see here it's being labeled as capital A. It's common to call them capital A, capital B, capital C. Those are common, but you can see any capital letter to label a matrice. So what else? Well, matrices are organized into rows and columns. So I want you to remember that rows go across and columns go up and down. Okay, so the way I remember this is that if you think about columns holding up a building, like one of those old school Greek buildings, those things are columns. And so if columns go up and down, then rows have to go across. That's how I remember it. You might have another way, that's fine. We need to talk about the order of a matrix. So the order is the number of rows by the number of columns. I think about this as the size of the matrix. It tells me how to build that shell and how to organize the numbers that go inside the matrix. So the number of rows, well, in this case over here, we've got 2 rows and 4 columns. So 2 rows, 4 columns. So that's a 2x4 matrix. Okay, last point we've got here is an element is an entry into one of the positions of the matrix. Matrix A will have an element Aij in the ith row and the jth column. So what does that mean? Well, that's a way of describing each of these numbers inside the matrix. So I've got a few examples here. So let's have a look. We've got A11 is equal to 2. So what does that mean? It means the entry or the element in position row 1, column 1. So if I find that for you, it's here in row 1, column 1, and we can see that's a 2. So that's position A11, and the value of the element is 2. Okay, let's look at the other 3 we've got here. We've got element 1, 2. So that's row 1, column 2, and that's row 1, column 2. So that entry is a 0. We've also got A21, which is row 2, column 1. So row 2, column 1. That's a 1. So that's checking out. And last one, we've got row 1, column 4. So row 1 is this top one here, and column 4 is all the way at the end, and that's a 3. Hopefully that's making sense. All right, let's take a look at some types of matrices. Our key takeaway here today is that there are many different kinds of matrices, and some of them have special names that explain their properties. First one we've got here is a row matrix, and that's sort of fairly autological. It is just a row. It's a matrix that only has one row. It can have many columns, but it can't have multiple rows. So here we see this is a 1 by n matrix. N is the number of columns. So in this case, this is a 1 by 4. Well, it has order 1 by 4. Okay, we can see it has some elements. Oh, sorry, there are 5. There are 5 elements there. My mistake. There's 1, 2, 3, 4, 5. So this is a 1 by 5 matrix. Okay, the elements in there aren't really important. I've put in 25, 32, 1, 9, 5, but we could put anything we like in there. Generally, we put numbers in there, but we could put letters to represent those things. So you could see a matrix that was like A, B, C, D, E, and that's fine too, so long as you know what those letters represent. All right, so next up, we've got a column matrix, and similar to the row matrix, that name makes sense. It's a matrix that only has one column. So I've said here it has order n by 1, so sort of any number of rows, but only one column. So I can see we've got 3 rows and 1 column, so that's a 3 by 1 column matrix. Again, I've just put random numbers in there, 16, 21, 4. Nothing special about those. I just needed to fill the spaces. Okay, onto square matrices. Square matrices are special. They have nice properties, and when we work with matrices, we love working with square matrices. We can do lots of cool things with them. And so lots of what you'll do will work with square matrices. So a square matrix has the same number of rows and columns. That makes sense, doesn't it? Because a square's got the same, length and width. They're equal. So the order of a square matrix is n by n. So n rows and n columns. So here I've got a 2 by 2 matrix and a 3 by 3 matrix. The numbers inside them aren't special. For now, what we're focusing on is their size and that they have the same number of rows and the same number of columns. Okay, even more matrices. We've got the zero matrix, symmetric matrix, and the diagonal matrix. So let's have a look at those. A zero matrix can have any order so long as all elements are 0. Okay, so zero matrix is like any matrix. You can build it however you like, so long as you only put zeros as the elements. So here I've got a 3 by 2 zero matrix and a 4 by 5 zero matrix. A zero matrix needs to exist for any size matrix. So if you can think of a matrix of some size, then you can put zeros in it and then get that zero matrix. So the simplest version would probably be a 1 by 1. So 1 row and 1 column. So that's the 1 by 1 zero matrix there. All right, symmetric matrices. What have we got here? We've got a symmetric matrix is symmetrical along the leading diagonal. What does that mean? The leading diagonal, I'm going to draw it on the tablet. So this is the leading diagonal here. It's the one that goes from the top left of the matrix down to the bottom right. And that's special. That's how we like to think of a diagonal matrix too. So we've got a diagonal matrix here, and you can see that in a diagonal matrix, we only have elements along that leading diagonal. So these are the leading diagonals in these matrices. Okay, looking at that symmetric matrix, what makes that special is that we can see that these values are reflected across that diagonal line. Not sure which way it is for you. For me, it's that way. So you can see this 9 in the top right is also in the bottom left, and this 6 in position, that would be in position row 3, column 2. You can see the position here, row 2, column 3 is 6. So those things have swapped. Okay, lots of matrices today. We've got an upper triangular matrix and a lower triangular matrix. These won't play too big a part in the general maths course, but they are very important later on. If you did some matrices at uni, then you definitely work with lower and upper triangular matrices, or I hope that you would. So we've got an upper triangular matrix is a square matrix, so it has to be a square, where all elements below the leading diagonal are 0. So we can see here in the upper triangular matrix that everything below this leading diagonal is 0. So you could think we only have sort of other numbers other than 0 above that diagonal for an upper triangular matrix. Okay, a lower triangular matrix is very similar. And so what we see is that above that leading diagonal, we have zeros. So that's the lower triangular matrix. It can get hard to remember which one's which. And so in this case, what we see is we sort of have values other than 0 below the diagonal. And that's why it's a lower triangular matrix, because the important numbers are below that diagonal. Okay, that makes a bit more sense with some context later on. So for now, just try and remember those definitions. All right, we've got a binary matrix. A binary matrix is any matrix that only contains 1s and 0s. So it can be of any size. You can make a matrix as big or as small as you like it, so any order. And the only restriction you have is it can only take in 0s and 1s. That's why it's called a binary matrix. You might know that a binary counting system only uses 0s and 1s. And if you're aware of some computing facts, then that should be a pretty easy definition for you to remember. Okay, last one, very special matrix, the identity matrix. We're going to talk more about the identity matrix as we go on. But what this one looks like is it is a binary matrix. It only has 0s and 1s, but it's special because it has 1s down the diagonal. So usually we label the identity matrix I, but there are many identity matrices. we have one for all square matrices. So here's a 2x2 matrix. The identity 2x2 matrix looks like this. Okay, so notice it's got ones down the diagonal and zeros everywhere else. Here's a summary of what we talked about today. We've got stuff about order of a matrix. That's pretty important. Remember that rows come first, columns come second. We've got square matrices, and we put the identity matrix here. These are probably the most important concepts today for you to remember, but we've got some definitions here that you could place in your bound reference if you like. Coming up next, we're looking at more matrices. So I'll see you there. Can you guess what we're trying to communicate here? If you're not sure, watch the video and come back at the end and see if you can tell what I'm getting at. Welcome to part 2 of Introduction to Matrices. In today's lesson, we're going to look at matrices and tables and how to generate a matrix using a rule. Let's have a look. Okay, matrices and tables. Our key takeaway today is that matrices can be used to represent the information in a table. The following table contains some of the running costs for Al's horse farm. So let's have a look. We've got adult horses and foals, so young horses. And we've got their expenses as shoes, feed, medication, and gear. The only thing that it costs for foals is that there's $100 a month for medication, compared to an adult horse where there's $400 a month for medication. So if you want to translate this information in the table into a matrix, then you just have to try and put the information in like a sensible spot. So here we've got some labels on the matrix, S, F, M, and G, and they correspond to these expenses up the top. And we've got A and F along the rows for adult and foal horses. Now, you actually don't need to make the rows the same necessarily, so long as you've got your information in a sensible way in the matrix. That's all good. What I should say is you might wonder what the purpose is here. Why not just have a table all the time? Why do we need to put the information in a matrix? Well, one reason for that would be that it's easy to feed a matrix into a computer or a computer program. And when we deal with real data, we're dealing with thousands and thousands of numbers. And a computer is really good at processing thousands and thousands of numbers. So if we give it to it in a matrix, then it can sort of work with that and give us back some information. So we're sort of practicing with simple matrices so that later on we can maybe do some more complicated things. Okay, here's a worked example. There are animals up for adoption at a pet shelter. We've got A is equal to this matrix here, and I've got some labels for young and adult animals, and we've got dogs and cats. Okay, so it looks like I've got some questions to answer about this matrix, so I've got to interpret it. Part A says, how many young cats are available at the pet shelter? So, okay, well, I'm going to go to cats, and I'm going to go, the other descriptor is young, so that's this entry here. So there are 3. Okay, how many dogs in total are available? Well, in that case, I need to look at young dogs and adult dogs. And so I'm going to add those 2 values. So 20 plus 5 is going to be 25. Okay, part C says, what information does the element A11 hold? So that's row 1, column 1. Okay, so there looks like row 1 is the young animals and column 1 is the dogs. So this contains how many young dogs? We might say the number of young dogs. Okay, what information does the element A22 hold? Because that's row 2, column 2, row 2, column 2. And I can see that's the number of adult cats. Okay, last one. Part E says, which element holds the number of adult dogs? Okay, so adult dogs is here, and I can see that's row 2, column 1. So the element would be A21. Okay, let's take a look at generating a matrix from a rule. Key takeaway today is that a matrix can be created from instructions related to its element's position. So I've got an example here to show you what I mean. This has come up in VCAR papers before, doing something like this, so I thought we should have a look. So the example, sort of like a question, it says, construct a 3x4 matrix where Aij is equal to I minus j. So how I do a question like that is first think about the matrix and what its order should be. So this is a 3x4 matrix, so it has 3 rows and 4 columns. And I've given an example of what I would draw out here. So I've drawn all the elements and where they belong. Then to work out what the value of those elements should be, I can do some working. So I'm going to work them out now. So if I want to know what A11 is, then I need to follow the instructions here of do I minus j. So I'm changing I for 1 and j for 1 in this case. So if I follow this rule, then that would be 1 minus 1, which is 0. And we can see here that that's the element that I've put in the first entry in the top left. Okay, so let's move now to maybe the next one in the row, which is A12. That means that I is 1 and j is 2. And if I do I minus j, then I get 1 minus 2, which is negative 1. And you can see that that element is in position 1, 2 in the answer matrix. Okay, so if we keep going, then if I do A13, then I is 1 and j is 3. So I do 1 minus 3, which is negative 2. I might just choose a random one now instead of doing them all. So let's take A32. I don't have to do them in order, so I can find them however I like. A32 would be, well, I is 3 and j is 2, and 3 minus 2 is 1, and so we can see that there's a 1 in position 3, 2. Okay, so, doing that, following those instructions, you generate a matrix. All the questions like this are sort of the same, and the only thing that gets harder is this rule. Let's have a look at another example. Here's another one, and I've put the shell there so I can put the matrix in easy. It says construct a 5 by 5 matrix where Aij is equal to Ij minus j. Okay, what I'm going to do is I'm going to find the top row first. I'm going to do A11, A12, A13, A14, A15. Okay, I'm going to substitute those values for I and j in this formula. Notice that I have to put j in twice. So I've got Ij, well that means I times j, and then I'm supposed to subtract j. So let's do that. I've got 1, 1. So I is 1 and j is 1. So I think I should have 1 times 1 minus 1, which gives me 1 minus 1 is 0. A12, I've got 1 times 2 is 2, minus 2 is 0 again. Okay, let's see if this pattern continues. I've got I is 1 and j is 3. So I've got 1 times 3 minus 3 is equal to 3 minus 3 is 0. Seems like that's going to keep happening. So I've got 1 times 4 minus 4 for the next one. Yep, that's certainly 0. 1 times 5 minus 5, 0. Okay, so the top row is zeros. Let's move on to the next row. Okay, the next row is row 2, so I should have element A2 and A21, A22, A23, A24, and A25. Okay, so following that formula, I need to multiply I and j and then subtract j. So I've got 2 times 1 minus 1. 2 times 2 minus 2. 2 times 3 minus 3. 2 times 4 minus 4. And 2 times 5 minus 5. Okay, let's work them out. So 2 times 1 is 2, minus 1 is 1. So I've got 4 minus 2 is 2. 2 times 3 is 6, minus 3 is 3. Oh, look at that. It's a nice pattern. So I get 1, 2, 3, 4, 5. And that's my next row. Now, you don't have to work them out in rows. You can work out any element at a time. But I'm going to keep doing this row thing because I think that's easy. Okay, next row should have the following elements. And the formulas I need are to multiply I and j and subtract j. So that would be these sums I need to work out. Okay, so let's compute all those values. 3 minus 1 is 2. 6 minus 2 is 4. 9 minus 3 is 6. 12 minus 4 is 8. And 15 minus 5 is 10. So you can see that pattern's going up by 2s. Okay, 2 more rows. Let's get them done. Okay, I've generated the sums that I need to work out for all of these elements. So let's do that now. Let's compute. We've got 4 minus 1 is 3. 8 minus 2 is 6. 12 minus 3 is 9. 16 minus 4 is 12. And 20 minus 5 is 15. That one's going up by 3, so let's put them in. Okay, and lastly, we've got row 5. So I've got 5 minus 1 is 4. 10 minus 2 is 8. I think you can see the pattern. 5 by 3 is 15, minus 3 is 12. Should be, I think, 16 and 20. Awesome. Okay, so the matrix is finished. Hopefully doing that enough times made you understand that we're just looking at the position of the row in the column and using that information to generate a value each time. Okay, so look out for questions like that. Okay, so in summary today, if you want to put the information in a table into a matrix, you can, and you should do it in a sensible way. And if you've got a rule for the element in a matrix, then you can generate that matrix from that rule. Coming up next, we've got some matrix operations, which you should have seen last year. So let's have a look at that. So yeah, wow, those are some matrices. Get it? Some matrices. Okay, let's move on. All right, should be some revision today. Let's look at operations with matrices. In today's lesson, we're going to look at the transpose of a matrix, sum and difference of matrices, and scalar multiplication. There's more operations than that, but that's what's in today's lesson. Okay, you might be familiar with the word transpose if you play music and you have to change the key of a song or something like that, or you might just know the word anyway. But transpose in mathematics, in terms of matrices, means to swap the rows and columns. So that's really all we're doing. If you have a matrix, then all the rows that you can see need to become the columns in that order. So the first row needs to become the first column. The second row needs to become the second column. The third row needs to become the third column, and so on. And it turns out that you can actually think about it the other way around. So the first column needs to become the first row, and the second column needs to become the second row, and so on. And that just works out to be the same thing with matrices because they're rectangles. So let's have a look here. If we have a transpose of a matrix, this means that if you've got an m by n matrix, so m rows and n columns, then A transpose, A to the power of t, or AT if you will be an n by m matrix. So we'll have n rows and m columns. So notice that those two have switched. And I think that makes sense. So here I've got a general matrix filled with letters A, B, C, D, E, F, and its transpose sort of looks like it's been flipped. So this first row, A, B, C, has become the first column. So you can see it's A, B, C running down now. You can also look at it that the first column, AD, has become the first row, AD. Okay, not much left to say there other than that, it's true that the second row became the second column, and the third column became the third row. So look at it however you like, so long as you're able to sort of do that process and reorganize a matrix for its transpose. The other thing to note here is that if you take the transpose twice, then you get back to the original matrix. So A transpose transpose is equal to A. So if we transpose this matrix, then we'll get back to where we started. And that should make sense too here. If we put that first row back to be the first column, and you can see that that's lining up there. Okay, I've given an example here. So here's A, which is equal to the matrix with column 15, 10, 5, and second column 7, 4, 21. Then its transpose will look like this. We've got 3 rows now of 15, 7, which was the first row, 10, 14, which was the second row, and column 5, 21, which was the third row. Pretty easy. Okay, here's a worked example. I'm going to do this by hand. So I've got a matrix M, which looks like it's a 4 by 5, and I need to find M transpose. So if M's a 4 by 5, its order was 4 by 5, then MT, or the transpose of M, or M transpose, should be 5 by 4. Okay, so I'm going to try and draw a shell that's going to hold 5 rows and 4 columns. So I think it should be a little bit longer than it should be wide. Okay, something like that. And I've got to make the first, you can do it either way, but I'm going to make the first column the first row. So I've put in -3, 2, 2, -10. Okay, and now the second column needs to become the second row. So I'm going to put down 4, 13, 2, 1 in that order. Okay, next one, 8, 8, 4, 0. Next one, 3, 0, 5, 5. And last one, 0, -1, 2, 9. When you do this, you don't have to circle the rows or circle the columns as you go. I'm just doing that so you can see what my thinking looks like. Okay, let's look at how to add and subtract matrices, or sum them and take their difference. So we've got matrices of the same order can be added or subtracted. Okay, so we can't add matrices that are different size, and we can't subtract them if they're a different size either. So they've got to sort of look the same for us to be able to add them. So if you want to add two matrices A and B, so here I'm calling this first one A and this second one B. A has entries A, B, C, D, and B has entries E, F, G, H. What you do is you need to add the elements in the same position. So here I've got in the top left corner, or in element A11, so row 1, column 1, I'm going to add that to the element in row 1, column 1 of B. And so you see here the resulting matrix is A plus E in that A11 position. Likewise, we add B to F, we add C to G, and D to H. So you can see there the resulting things there. So if you want to subtract, it's the same process. We've got matrix A subtract matrix B, and we've got A, B, C, D, and E, F, G, H, so the same matrices as before. I'm going to do A minus E to get that first position. I'm going to do B minus F to get that next position, and so on. So here's some examples. I've got three matrices A, B, and C. A and B are both 2 by 2 matrices, and C is a 2 by 1 matrix. Okay, so my example, I'm doing A plus B, B minus A, and A plus C. So first one here, I've got A plus B. I've got matrix 1, 2, 3, 4 plus 3, 3, 4, 4. So adding these positions, 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 4 is 7, and 4 plus 4 is 8. Okay, if you want to do B minus A, then same sort of thing. We're going to do 3 minus 1. That gives me 2. 3 minus 2 is 1. 4 minus 3 is 1. And 4 minus 4 is 0. That one's done. And finally here we've got A plus C. So I've got the matrix 1, 2, 3, 4 plus the matrix 5, 2. In this case, we can't do it. We can't add these matrices. This can't be simplified. We can write the expression A plus C, but we can't compute anything further from here. It's important that you know this fact, that you can't add matrices of different order, because VCA will test you at some point here. They'll try to give you two matrices that can't be added or subtracted, and you have to sort of know that that doesn't work. Okay, here's a worked example, one for me to do. I've got matrix A and B. They're the same size. They both have order 2 by 3. And so I'm supposed to do A plus B and B plus A. I've also got the calculator here so we can see how to add them. So I'm going to do it by hand first. So here's A plus B. So I can write A plus B is equal to 0, 1, 2, 3, 4, 16, and plus matrix B. There it is there. So my resulting matrix should be 2 by 3. So I'm going to draw that 2 by 3 shell. And so I've got 0 plus -2. So that should be -2. 1 plus 5 should be 7. And 2 plus 108 should be 110. Okay, next row, let's add them. We've got 3 plus 16, so that should be 19. 4 plus 19, so that should be 23. And 16 plus 17, which I think should be 33. Okay, we've also got B plus A, and there's a reason I did this. When you're used to adding numbers, you know that 2 plus 3 is 5, and you know that 3 plus 2 is also 5. So it doesn't matter what order you add numbers in. And so here we're trying to investigate, well, does it matter what order I add matrices in? The answer is that it doesn't. So I'm going to do B plus A here, but I should get exactly the same thing. Here's matrix B plus matrix A. I'm going to draw them out. Okay, so there's the matrices in the shell for the resulting matrix. Again, I'm adding them. -2 plus 0, well, that's -2. 5 plus 1, that's 6. Oh, I made a mistake the first time. It should be a 6 there. Okay, 108 plus 2, that's 110. And 16 plus 3 should be 19. 19 plus 4 should be 23. And 17 plus 16 should be 33. Okay, so looks like we got the same answer after I corrected my mistake. And now we can use the calculator to see how to do that. So I'm going to pull up the TI. Okay, so I've put the matrices in there. I've made them the right size, and I've put all the entries in, the elements, sorry, and I'm adding them. Okay, so I press enter, and I get that matrix that I expected to get. Now, I could do this again with B plus A, but I think we can all see that it would be the same, so we won't bother. Let's have a look how to do it on the Casio. Here's the Casio, so let's put the matrix in. Okay, so I've put the matrices in the Casio, almost exactly the same, and just press execute, and we get our matrix. Great. Okay, here's another worked example. I've got A and B again. They're the same matrices as before, except this time subtracting them. So I've got A minus B and B minus A. Now you might know that subtraction isn't a commutative operation, so that if I do 4 minus 2, well, that gives me 2. But if I do 2 minus 4, that gives me negative 2. So it does matter the order I do subtraction. And with matrices, it's the same, because I guess we're subtracting the elements within those matrices that this property still sort of, I guess, doesn't hold. They're not commutative objects. So let's see that we get different answers for A minus B and B minus A. So if I take A minus B, I'll do this one by hand, I'll write it out. Okay, so let's do this. I've got to do 0 minus negative 2. Okay, so I think that should be 0 plus 2, which is 2. I've got 1 minus 5 would be negative 4. I've got 2 minus 108, so I think that should be negative 106. And 3 minus 16, negative 13. 4 minus 19 should be negative 15. And 16 minus 17 should be negative 1. So there's the matrix I got there. Let's have a look at B minus A and see what we get. So I'll write out the matrices again. Okay, there they are. Let's do the subtraction. I've got negative 2 minus 0 should be negative 2. So notice that this matrix is already different. Okay, we've got 5 minus 1 should be 4. 108 minus 2 should be 106. 16 minus 3 should be 13. 19 minus 4 should be 15. And 17 minus 16 should be 1. Okay, so what you might notice is that this answer is negative 1 times that matrix. And you might like to think about why that is. Okay, we can also do this with the calculator. We'll just do it with 1 because it's pretty much the same on both. So let's have a look at the TI. Okay, I've already got these matrices, so I might use them from before. So I'm going to do A minus B. So I'm going to take all of this, Control C and Control V. And I'm just going to change that plus to a minus. Okay, and looks like I got it right. We're getting A minus B is the same matrix there. Okay, last operation for today is scalar multiplication. And so what you should know is that matrices can be multiplied by a scalar. So if you do physics, you might know the difference between vectors and scalars. It turns out that matrices are a kind of vector. And you don't need to worry about that just yet. If you're interested, maybe you should go and have a look. But today, what a scalar is to us, we would just think about as a number. Okay, so you can think about this as a number and any real number you can think of. So it could be 2 or 3 or 4, or it could be negative 5, or it could be a fraction like 4/5 or 1/3 or 1/2, or it could be something harder like pi or square root of 2. And if you're doing specialist maths, this could actually even be a complex number. So something uglier like square root of negative 2. We don't really need to get too worried about this. Let's just think about, for general maths, a scalar being a number. So if I have a matrix A, where the elements are A, B, C, and D, I can multiply that by some number K. So if I have K times A, then that would be K times the matrix A. And What I do is I multiply that number to every element inside the matrix. So I get K times A, K times B, K times C, and K times D. If that's all too many letters for you, let's have a go with some numbers. So here we've got another example. I've got matrix B. It's got 2, 1, 6, 4, 8, 9 as elements. We're going to find 4 times B. So if we have B and we have 4 times B, then what I need to do is multiply all those elements by 4. So I get 4 times 2, 4 times 1, 4 times 6, 4 times 4, 4 times 8, and 4 times 9. And if we can do that multiplication, then we should get the matrix 8, 4, 24, 16, 32, and 36. Here's a worked example for us to try. We're going to see that the CAS can do this for us, but we should still know how to do it by hand. So we've got A equals the matrix 0, 1, 2, 3, 4, 16. And I'm going to times it by -5. So if I want to do that, I'm going to write -5A is equal to -5, and I can just draw that next to the matrix, and it means to multiply it. We can hide that multiplication sign. Okay, so now we've got the matrix, and I need to multiply all those numbers by -5. So I'm going to do that. So 0 by -5 is 0, 1 by -5 is -5, 2 by -5 is -10, 3 times -5 is -15, 4 times -5 is -20, and 16 times -5, I think, should be -80. All right, so let's pull up a calculator and see how to do this. We just literally put the matrix in and multiply it by that number. So let's pull one of them up. Okay, I'm going to put the matrix in by going Menu, Matrix, Create, Matrix, and I need a 2 by 3. Okay, there it is. So I'm going to put all the elements in. I'll do that now. Okay, so there's our matrix. We want to multiply it by -5. It doesn't matter which side we multiplied on, but to keep in the fashion of what we've just done, I'm just going to click here and do -5 times that matrix. Okay, let's press enter, and there's our answer. Now that's exactly the same in the Casio. Okay, here's a summary of what we talked about today. We've got the transpose, we've got adding matrices, we've got subtracting matrices, we've got multiplying by a scalar. Up next, we're going to multiply 2 matrices together and look at doing that repeated times, and that's the matrix power. So we'll leave that there for you to take some notes if you'd like to. If you've played around in PowerPoint before, you know you can animate things. And so we've got this matrix here, which spins and then waggles and then grows. So all of those animations there are examples of linear transformations. And you can tell a computer to do these animations using a special matrix. And that's cool. It's really one of the awesome things about learning linear algebra. So if you get a chance to learn some and you feel up to the challenge of doing it at uni, then it's a great mathematics subject that you should check out. Here's advanced operations with matrices. Today we're looking at matrix multiplication, summing matrices, and powers of a matrix. So last lesson we looked at adding matrices, subtracting matrices, and we did scalar multiplication. And that's when we did like 2 times a matrix, and then every element in there was multiplied by 2. But today we're looking at multiplying 2 matrices, and that's different. So let's jump in and have a look. Okay, the first thing to talk about when we talk about matrix multiplication is the order of matrices. And so you probably remember from last year that the order is given by the number of rows by the number of columns. So that's, we'd say, like an n by m matrix, n meaning the number of rows and m meaning the number of columns. So the reason we need to talk about order is because that is what defines whether or not we can multiply the matrices, whether matrix multiplication has been defined for those 2 matrices. The order of the matrices to be multiplied determines whether matrix multiplication is defined. Matrix A of order n by m can be multiplied with matrix B of order m by l. So the first thing here is that I've got 2 matrices, and this one is n by m, and this one is m by l. If I want to multiply them, then the number of columns in the first matrix needs to be the same as the number of rows in the second matrix. And that will give us an n by l matrix. So this third dot point here, I've got matrix A multiplied by matrix B will result in matrix C with order n by l. So that's the other thing. So here, if we're checking if 2 matrices can be multiplied, we want to write out their orders. If these 2 inside match, then we can multiply. But also, these 2 outside numbers tell us the order of the resulting matrix. So here, we know that C will be an n by l matrix. That's useful because when you do matrix multiplication, you sort of need to draw out the shell. So we want to know how large that shell should be before we start multiplying. So that's the sort of the first step. Okay, to multiply two matrices, the number of columns in the first matrix must be equal to the number of rows in the second matrix. Okay, so that's sort of a description of looking at the orders there. I guess when I do this in practice, I do write out the orders and then I check, can I multiply them? And then I check how large should the answer should be. So here I've got some abstract example of a 2 by 2 matrix multiplied by a 2 by 1 matrix. Now I don't have to write that times symbol in there. If two matrices are next to each other, it's implied that they're multiplied. So first of all, I check, can this one be multiplied? Yes, it can, because the number of columns in the second matrix matches the number of rows in the second matrix. And I can see the resulting matrix will be a 2 by 1, which is this one here. Okay, so that's the size of the resulting matrix. Let's move on and see if you can have another go. Okay, so here's two matrices A and B. Determine if the following matrices can be multiplied. Okay, so can I do it? The answer is yes, in a certain way. How do I know that? Well, I wrote the question, but let's look. Can I multiply A by B? That would look like matrix A, 1, 2, 5, 2, multiplied by matrix B, 3, 4. Okay, so I'm going to check their orders. I'm going to write them underneath. So this is a 2 by 2, and this one is a 2 by 1. So yes, the inside numbers match. The number of columns in A is equal to the number of rows in B. So I can multiply. Or we might say matrix multiplication is defined for AB. However, we can't do B times A. This would look like 3, 4 times 1, 2, 5, 2. And here if we write the orders underneath, we get a 2 by 1 and we get a 2 by 2. And so because these two numbers, the inside ones, don't match, matrix multiplication is not defined for B times A. Here we see an immediate difference between matrix multiplication and regular multiplication that you're used to. So you know that with regular numbers, 2 times 3 would be 6 and 3 times 2 would be 6. What this property of like the order not mattering is called is the commutative property of multiplication with real numbers. With matrices, matrices don't commute. A times B is not necessarily B times A. We can find some matrices that rule applies to, that the order won't matter. But for most cases with matrices, I would say that A times B is not the same as B times A. To answer this question, it says determine if the following matrices can be multiplied. Well, yes, they can. That's the answer. But it has to be A times B, not B times A. Okay, here we can determine if the following matrices can be multiplied. I'm going to show you how to do it with your CAS calculator. We could do this one by hand in the same fashion, but we're going to use the calculator and see what it says when we try. Okay, here's my TI. I'm going to go menu, add calculator, and I want to put in some matrices. Now, I tend to use the class pad actually. That's the other calculator. So I don't know if I'm doing this the fastest way, but here's how I do it. I go menu, matrix, create, matrix, and then I get a prompt that says like, how large do you want this matrix to be? What order do you want? So I've got a number of rows is 2. Well, if I'm going to make A, that's 2 rows and 3 columns. So I'm going to make A first, and now I'm going to put in the numbers. So let's do that. Okay, and I want to multiply this to matrix B. So I'm going to create another matrix. So I go menu, matrix, create, matrix, and B is a 3 by 2 matrix. So I want 3 rows and 2 columns. And now I can put in the numbers. So that's going to be 1, 1, 2, 1, 3, 1. Okay, now my calculator can multiply matrices. And so let's hit enter. And hey, look like we got an answer. So if we did AB was equal to 1, 2, 10, 5, 2, 4 times 1, 2, 3, 1, 1, 1. And we got a 2 by 2 matrix. So here we can see a 2 by 3 times 3 by 2 matrix. It was allowed, those two match, and the size was a 2 by 2. And that resulting matrix was 35, 13, 21, and 11. Okay, so we did it. The answer is yes, they can. We could say AB is defined, or AB is the matrix that we found. Can we do BA? Let's chuck it in. Well, now I've already got these ones here, so I'm just going to copy and paste them. So I copy that one there, and I'll copy this one here. So I've got BA now, and if I do that, I get a 3 by 3 matrix. So I can say AB is defined, and BA is 2. Notice that AB and BA aren't the same matrix. They're not even the same size. So that should further solidify that AB is not necessarily BA. Okay, in this question, I'm supposed to explain why AB is undefined. And to do this, you need to understand that when I have AB, I mean this is the same as A matrix multiplied with B. So how do I do that? How do I explain why AB is undefined? Well, I need to use the order. So the order of A is a 2 by 1. And this is supposed to be matrix multiplied to B, which has an order of 2 by 2. And so here we can see that the inside numbers don't match. So how do I say this? Well, I could say AB is undefined as the number of columns of A is not equal to the number of rows in B. Okay, I've got the calculator here because I want to show you what the calculator says when it can't do the multiplication. Okay, we're going to quickly make that matrix, we're going to make both of them and see just the error message that we get here. Okay, so there's A, and let's make the other one. Okay, so there's AB, and if I press enter, I get this error. It says dimension error, a list of matrix index is not valid. For example, if something is this or whatever. So it gives me some error message. And so this dimension error here, that's a clue that there's something wrong with the dimensions of your matrix, okay? So usually an error message in your calculator is trying to tell you what's wrong. So you should learn to try and read that and try to think about what might have happened. A mantra I like to tell my kids is that CAS always works. And that's not true, but most of the time when a student's having a problem is that there's some error in putting in something to the calculator, or there's just something more that we need to do to get the computer to do what we ask it to. So I want to show you an error message and how we can use that. Okay, let's move on. Okay, onto matrix multiplication. You might have seen this last year, but it would be pretty normal if you needed a review of how to do this. Might have been a while since you have done it. What I'd like to say about matrix multiplication is that the first time you learn this, I guess it's usual that someone teaches you this method of sort of like walking along the rows and the columns. And so someone would say like, oh, go along here, then down there, and that's the first entry, and then go along there again, and then do that one, and that's the second entry, and then drop down a row and go along there and go down there, and then that's the next entry, and then one more time along that row to do all the columns, and then that gives you the last one. And while that's great and building it up sequentially, and you should totally learn to do that, it's important to have a flexibility and be able to actually work out any element at any time. And so if you remember that you sort of have to multiply and add the things as you go along, then if I circle any element in the matrix, then its row and column position represent the row and column in the initial matrices that I have to take the dot product of. So what I mean by that is if I want this position in 2, 1, in row 2, column 1, that means I need to take the sequential products of row 2 and column 1 and then add them together. It's a lot easier with an example, and we're going to see one in just a moment. But so that's how we've done it. What I've got here is a diagram that shows you how to get each entry here in the matrix. So if we do A times B, give us a matrix C, then if I've got these matrices here with A, B, C, D, E, F, G, H in them, and they're just numbers, then to get this first position, I need to do A times E, and then move it along and do B times G, and then add those two together. Likewise, if I want any other position, say I want this one here in row 2, column 2, then I need to work with row 2 and column 2 in the first matrix. So I've got here this position, C22, is going to be C times F plus D times H across the row and down the column. Again, we said in the last slide, unlike multiplication with numbers, matrix multiplication is not commutative. This means that AB is not BA. Okay, let's look at a real example. It's normal if you have done matrix multiplication, learned how to do it, sort of done what teacher said, and then not really understood why we want to multiply in this way. Matrix multiplication is really great if we want to multiply and then add. So I've got a fake cafe here that serves 2 items. It serves Eggs Benedict and Big Brekkie. And in the Eggs Benedict, it looks like you get 2 pieces of toast and 2 eggs, okay? And in the Big Brekkie, it looks like you get 2 pieces of toast and 1 of each other item. You get 1 egg, 1 piece of bacon, or 1 serve of bacon, and some avocado. Okay, and you can see this other matrix here is my cost matrix. So this was the number of items that we need to prepare, but this matrix here holds the cost. And why that's useful is that if you want to figure out how much something costs, you'd say, well, how much does one piece of toast cost? And how much does one serve of eggs cost? And then how many serves did you give those people? What you'd do is you'd multiply those two numbers and then add the cost together at the end. So we're going to get the total cost here of the whole meal to buy or to serve, I guess. What we're going to do is we're going to actually do this multiplication by hand and show that we can get these numbers. And hopefully doing that sequentially helps you understand why that's useful. Okay, so I'm supposed to, I can see the answer here is what I'm going to get, but I'm going to just run this multiplication up here. So I've got this matrix. I've got 2, 2, 0, 0, 2, 1, 1, 1, and my cost matrix is 1, 0.5, 2, and 40. Okay, so let's do this. I can see that this is a 2 by 4 matrix, and this matrix here is a 4 by 1 matrix. So I can multiply, great, and I'm going to get a 2 by 1 matrix. So that's how I've drawn this shell here as a 2 by 1. If I want this position, the first position in row 1, column 1, then I need to take the sequential products of row 1 and column 1. So I need to work with those two. So I sort of walk along the row and multiply as I go. So I get 2 times 1 plus 2 times 0.5. Okay, and I actually might need to go a little bit bigger to the next one. And now if I want row 2, column 1, then I need to multiply along row 2 and down column 1. So I get 2 times 1, so that's 2 pieces of toast times the cost of 1 piece of toast. That gives me 2 times 1 plus 1 times 0.5. So 1 times the cost of an egg, which is 50 cents. So I do 1 times 0.5. And then move along again. I've got 1 times, so I've got 1 piece of bacon times the cost of bacon. So plus 1 times 2. And finally, I've got 1 times the cost of avocado, the reason we can't afford houses. So we've got 1 times 40. And so when we work out that final matrix, you can sort of see where that large cost came from. It came from timesing 1 avocado to its cost. And so here in the top 2 plus 1 is going to give me a cost of 3. And 2 times 1 is 2, plus 0.5 plus 2 is going to give me 4.5 plus 40 is going to give me $44.50. So that's why matrix multiplication is the way it is. It's a convenient way for us to, well, not because of cafe items, but sometimes we want to multiply and add sort of in one operation. And that's what matrix multiplication does for us. In reality, a lot of people use matrices for big sets of data, and sort of running this sum and product functions together is really good for doing lots and lots of multiplications all at once. So matrices is super useful for encoding stuff into a computer. Okay, here in this example, I'm going to find A, B, and BA and verify that AB does not equal BA. Now, I'm going to do this by hand, and I'm going to do it with the CAS, just so you can see me calculate by hand. Even though in general maths we always have the CAS calculator with us in our exam, you still need to know how to do this by hand. So you should practice by hand. The reason for this is because some VCAR questions can force us to need to know how to do it by hand. They're sort of clever enough to write the questions that we won't be able to get the answer just by using the CAS calculator. So, okay, let's do it. I've got to work out A, B, and BA, and they're both 2 by 2 matrices, so I can see they can be multiplied, and they're going to give me a 2 by 2 matrix. So I'm not going to do that order step. I'm just going to jump in and work out A, B, and BA. So, okay, so AB is going to be that matrix 1, 2, 5, 2 times B, which is 3, 4, 2, 2. Okay, so my resulting matrix is going to be a 2 by 2. So let's do that here, 2 by 2. I'm going to have to go across this row and down this column. So that's 1 times 3 plus 2 times 4. So 1 times 3 is 3, and 2 times 4 is 8, and putting them together gives me 11. And now I need to work out this number here, which is in row 1, column 2. So I need to multiply row 1 and column 2, or take the dot product if you want to be correct. So, okay, let's do it. So I've got to do 1 times 2 is 2, and 2 times 2 is 4. 2 plus 4 is 6. So I could write it all out, but I can sort of do this in my head. And if you can too, I think that's fine. Okay, next one in dark blue. This is in row 2, column 1. So I want to find the entry in row 2, column 1. So I need to look at row 2 and column 1. So let's do that. 5 times 3 is going to be 15, and 2 times 4 is going to be 8. So 15 plus 8, I think it's going to be 23. Last one, I'm in row 2, column 2. So to find that entry, I need to look at row 2, column 2 in the first two matrices. So, okay, I've got 5 times 2, that's 10, plus 2 times 2, that's going to be 4. So in total, I have 14. Okay, so that's my final matrix there. Awesome, lots of colors, that's cool. Now I need to do BA and verify that it's not the same as AB. So let's do that. I'm going to find BA. Okay, I'm going to write it out. 3, 2, 4, 2. And this one's going to be 1, 2, 5, 2. And I'm going to get a 2 by 2 matrix. Now, last time I did it in the order sort of you might be used to. I'm actually going to do it backwards this time to show you that you can just work out any entry at any time. So, or maybe I'll just do it out of order in any way I feel like. Okay, I'm going to find this entry down here first. That's in position 2, 2, or row 2, column 2. So I need to look at row 2 in the first matrix and row 2 in the second matrix. So 4 times 2 is 8, plus 2 times 2 is going to be 4. So 8 plus 4 is 12. Okay, so I'm really used to looking sort of across and down. All right, I'm going to choose a different matrix, different color, and I'm going to choose this one here. I'm going to do the one above it. That's in row 1, column 2. So let's do that. I need to look at row 1, column 2. So I get 3 times 2 is 6, plus 2 times 2 is 4. 6 and 4 together make 10. Awesome, just 2 more. I can already see that it's not the same matrix though. We're getting different numbers in different positions, so it can't be the same. I'm going to choose this one here. That's in, what is that in? That's in row 2, column 1. So I need to look at row 2, column 1. And going across the row and down the column gives me 4 and 1 makes 4. 2 and 5 makes 10. That's a total of 14. All right, last one, different color. This one is in row 1, column 1. So let's look at row 1, column 1, 3, 2, 1, 5. So what do we get? 3 times 1 is 3, and 2 times 5 is 10. It gives me a total of 13. And what I need to do here to verify that AB does not equal BA, I've got a chain here of BA, so that's BA equals this, which is equal to this thing here, and that is not equal to 11, 6, 23, 14, which was AB. And here I can see I've got a chain from BA, something that's not AB. So I can say, therefore, BA is not equal to AB as required. When you learn mathematics, a really common thing for students to do is once you know one way to do something, you're reluctant to try another way. And largely, that's really an effective way for learning. You go, okay, well, I know how to do this type of problem, and I can do it this way, so I'm just going to practice that way and make sure I can do it for the exam or whatever. What I would say here is if you've learned one way of doing matrix multiplication, also you should learn how to just get one element. That's important that you can do both things. Both of those are separate skills, and it's easy to sort of be like, oh, well, I can multiply them. I don't need to do it out of order. I would say that you do need to be able to do that. And so I encourage you to practice both methods. You need to be able to do both. Finally, I've got the calculator here to show you that we can do this really quickly with the calculator. So, okay, there it is. And I need A and B, so let's put them in now. Okay, so I just did AB, so we can see that one there is done on the calculator. Awesome, looks like I got it right before, which is promising. So let's do the other order now. I can just copy and paste these using Control-C and Control-V and press Enter. And looks like I got the same answer there too. Okay, so you can see that doing a different order doesn't give you the same matrix, and important that you know that. Okay, on to summing matrices. The key takeaway today is that a summing matrix is a row or column matrix where all the elements are 1. Summing matrices can be used to add the elements in a row or column of another matrix. So I've got an example here. So a column matrix can be post-multiplied to sum the rows of a matrix. So here I've got this matrix from before times the column matrix 1, 1, and that's going to add up the rows. So we can see here that 1 times 2 is going to times by 1, and so we get 1 times 1 is 1, and 2 times 1 is 3. So we get that option 3. So you should do this by hand and verify that that's sort of making sense to you. And so, yeah, so you can see, like, let's verify that it worked. So 1 plus 2 is 3, 0 plus 3 is 3, 1 plus 0 is 1, and 4 plus 5 is 9. So that matrix did indeed add up the rows. Okay, if you want to do the other way, a row matrix can be pre-multiplied to sum the columns of a matrix. So if we take a row of ones of the right order and multiply it to this matrix, then we'll add up the columns. And so how that works is, okay, so say I want this position, I have to look at the first row, first column. So first row, first column, we go 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, and 1 times 4 is 4. So you can see the ones in the sum matrix just serve to give us back that number in the column, and then we're supposed to add them all as matrix multiplication is defined. So again, 1 plus 1 plus 4 is 6, and that's worked effectively. So you could do that by hand and see how and why it works. I think the last thing I have to say here is that if you're not sure which one to use, say if you want to add up the columns, say you wanted to add these columns, well, you're going to need a 1 by 2 matrix. So you've got to ask yourself the question, well, how can I get a 1 by 2 matrix? Because this is a 4 by 2, and I need to get a 1 by 2. So I need this number in the back, and so you can sort of work backwards to see that, well, I need this number to be a 1, and in order for it to be defined, I need the number in front to be a 4. So sort of using your knowledge about orders of matrices, we can see if we need a row or a column summing matrix. Hopefully that makes sense. Okay, onto powers of a matrix. If you've worked with powers before, or exponents or indices, you probably remember what they mean. If I had 2 squared, this would be 2 times 2. If I had 2 cubed, this would be 2 times 2 times 2. 2 to the power of 4 would be 2 times 2 times 2 times 2. So it's the number of times you multiply something by itself. And the concept here is exactly the same. If you have a little number up the top, a superscript, then that is indicating a power or a repeated multiplication. Now, it is slightly different here, because we're multiplying matrices, so it's not the same as multiplying numbers, but essentially the idea is the same. So let's read our key takeaway. A square matrix can be raised to a power by repeatedly multiplying the matrix by itself. Okay, so it turns out we can only take powers of square matrices. The matrix must be square so that the repeated multiplications are defined. Okay, so here I've got a squared is a times a cubed is a times a times a, and a to the power of n is a times a times a times a times a n times. Okay, but let's delve a little deeper into that second dot point. What do I mean? The matrix must be square so that the repeated multiplications are defined. Okay, let's say that A is a 2 by 2 matrix. Okay, if I want to do A squared, then this would give me a 2 by 2 times a 2 by 2. Notice that here the insides are the same, and so we can square a matrix that's 2 by 2. If I take another example where A is not, or so a different matrix, so let's say I've got a 2 by 3. So there's our 2 by 3 matrix. If I try and do B squared, this would be a 2 by 3 times a 2 by 3. And that doesn't work because the insides don't match. The number of columns in the first matrix isn't equal to the number of rows in the second matrix. So, what you can think about is that if you're going to square this matrix, then you need both of these to be the same so that it lines up and it's defined. And that's, the same logic for doing this more and more times. If we can't square, I guess here we're squaring a square matrix. But if we're trying to cube a square matrix, the problem is still the same. We do need to be able to square a matrix before we can cube it. And that's because a matrix cubed is the same as a matrix squared times itself. So see, we have to calculate the square before we can calculate the cube. Hopefully that makes sense and it wasn't too much maths. Yeah, here's an example. I've got A is the matrix 4, 5, 2, 1, and we can calculate A squared by doing A times A. If you go through these calculations, let's just do one of them. That was 26 apparently. So I've got 4 times 4 is 16 plus 5 times 2 is 10. 10 and 16 make 26. So that's checking out. Okay, the rest will work. Notice here, if I've got A cubed, I've got A times A times A, and I've got to choose 2 of them to multiply first. It actually doesn't matter which 2 you choose. You can do these 2, or you can do these 2. And that's because that matrices are what's called associative. We don't need to do that in this course, I think. Just know that you can do either order you like there. You will get the same answer, which is cool. And so here we've done these 2 first. So they've worked out those 2 to give us A squared, and times that by A again gives us A cubed. So you should definitely practice doing some of these by hand when you're doing your questions.
All right, that's our lesson on multiplying matrices. Here I've given an example of a 2 by 2 matrix, but you should make sure you can compute up to 3 by 3 or 4 by 4, and it's worth doing that by hand until you're really comfortable in doing it. Really, the CAS, I think, you need to learn to use that too to go fast in your exam, but don't neglect the practice by hand. That's really important. I've got some stuff on summing matrices there and stuff on powers of a matrix if you want to take some notes in your bound reference. And coming up next, we're looking at inverse matrices. So I'll see you there. Hi. Today's lesson is sort of about opposites. If we think about numbers, +2's opposite is maybe -2, and the opposite, you could think of the opposite of 5 as 1/5 as well, depending if you're trying to multiply or add numbers. This concept of opposites we sort of refer to as inverses in mathematics. And so I was looking for an example of opposites, and I came across this beautiful Dalmatian, and I used to have a Dalmatian when I was younger, and her name was Pepper, and she had blue eyes just like this one. Well, actually, she had 2 blue eyes. If you look closely, this Dalmatian has 1 blue eye and 1 brown eye, so it's pretty hard to go past this beautiful dog. If we look at this dog, a Dalmatian is white with black spots, but if we take the inverse of that, then we get a black dog with white spots, which I think is pretty cool. Okay, let's dive in and have a look what matrix inverses look like. All right, so welcome to inverse matrices. Today, we've got 3 main points to look at. We've got inverse matrices, the determinant, which is something that we need to find the inverse, and the definitions of singular and non-invertible. All right, let's have a look. Our key takeaway today is that a square matrix A may have an inverse read as A inverse, such that A times A inverse is the same as A inverse times A, which is the identity matrix I. A 3 by 3 identity matrix looks like this. That's one where there's zeros everywhere except on the diagonal, and they're all ones. So hopefully you remember the other identity matrices. The 2 by 2 one looks like this, and I could draw the 4 by 4 one, and it looks like this. So hopefully you remember what an identity matrix is. And we're going to just have a little quick chat about why those things are called what they are, and how you've actually seen inverses and identities for a very long time. What I'd say is that the best analogy here for matrix multiplication inverses would be an inverse just with numbers. Okay, so what makes something an inverse? Well, let's take 2 times a half. What is 2 times a half? You probably know that the answer is 1. Okay, and why is that special? We'll take 3 times 1/3, and that also gives you 1. So 3/3 are 1. And I could do this again with some harder number. I could do 12 on 7 times 7 on 12. And if you're good at multiplying fractions, you might realize that that is also 1. And so it turns out that a reciprocal is a whole numbers, a reciprocal is any number, any real numbers inverse. So why is this? Why are they called the inverse? And it's because they land us on the identity. Okay, so an identity in mathematics is something that sort of does almost nothing. It returns what we have. So why is 1 special? You know this property of 1. 2 times 1 is 2. 3 times 1 is 3. And 12/7 times 1 is 12/7. That is, that multiplying by 1 doesn't really do anything. It gives us back the number we had. And that's why it's called an identity. An identity is a common idea in mathematics spread across lots of different areas. And here, the identity matrix, you might know that if I times something by the identity matrix, I get back that matrix. So if I had this matrix here, 2, 1, 1, 1, if I did 2, 1, 1, 1 times the identity, then I would just get back this exact same matrix. And you can test that by hand to verify that it's true. And the special thing about the identity is it doesn't matter what side I multiply that on. So if I did that same calculation but with the identity in front, I would also just get that matrix back. Okay, so that's why an identity is special. It returns the thing that we had when we do some operation. So that's cool. Here, the inverse is going to return the identity. Okay, I've cleaned up the slide a little, and I've got A and A inverse here. So I've actually gone to the trouble of finding the inverse of this matrix, so we can show that when we multiply them, we get the identity. So here I've got A, which is 2, 1, 1, 1, and the inverse supposedly is 1 times -1 times -1 times 2. And I'm going to verify that that A inverse is the inverse of A. And the way I'm going to do that is I'm going to multiply them. and I'm going to show that it gives me the identity. So let's do that. Let's do I might write this out. Let's do A times A inverse. So that's going to give me 2, 1, 1, 1 times 1, negative 1, negative 1, 2. Okay, so I've got 2 by 2 matrix times a 2 by 2 matrix, and that will give me a 2 by 2 matrix. So let's work out that first position. I'm going to have to go across this row and down this column. So that's 2 times 1 is 2, plus 1 times negative 1 is minus 1. So that gives me 2 minus 1 is 1. Okay, now I need the next position. I've got the next position, I need to do row 1, column 2. And so that's 2 times negative 1 is negative 2, plus 1 times 2 is positive 2. So negative 2 plus 2 is going to give me 0. Okay, that same thing's, almost same thing's going to happen here. I need this position here in row 2, column 1. And that's going to be 1 times 1 plus 1 times negative 1, which is negative 1. So 1 minus 1 is going to be 0. And last position here is in row 2, column 2. And so I need to look at row 2, column 2 in the first two matrices. Got 1 times negative 1 is negative 1, plus 1 times 2 is 2. Negative 1 plus 2 is going to give me 1. And so that is I. And I can actually stop there. I've verified. So A times A inverse did give me the identity. So A inverse is the inverse of A. Okay, so I tested it and it worked. You could also check the other statement. We don't actually need to. It is true that we've found one way, the other way will work. In this case, for an exercise, I might leave that to you. Can you do the same calculation with A inverse in front and see that you do get I? All right, let's move on. Okay, here's a worked example. We need to find M inverse of this 3 by 3 matrix here. There is a way to do this by hand, but we don't do it in the general maths course. So we're going to just do this with a calculator. It's super easy. We're just going to type in the matrix and put it to the power of negative 1. And our CAS knows that to work out the inverse from doing that. So let's pull up the calculator. Just one matrix to add in today. So let's put in a 3 by 3. And I'm just going to type in those values. So we get 24. Okay, there's my matrix. And now I'm going to raise it to the power of negative 1, which my calculator knows to read as find the inverse. Okay, there it is there. Then we get that matrix. And there it is on the screen. It's pretty ugly. Lots of fractions involved, but that's okay. That's just the answer. So let's work it out. It's going to be 10 on 207, 14 on 207, negative 19 on 414, 7 on 414, 67 on 207, negative 17 on 414, negative 4 on 207, negative 47 on 207, and 49 on 414. Now, that's the answer, and it works. But sometimes when we get tricky numbers like this, we can doubt ourselves. And a way we could check to see if this works is to multiply it by the original matrix. And if we get the identity, then we know we're right. So let's take this matrix, and let's copy this matrix and multiply them, and we should get the identity. And you see that we did, so we know that we're right. Okay, so we used our calculator to find an inverse matrix, but we also need to be able to work this out by hand. So our key takeaway here is the determinant is a number associated with a matrix. It is used to calculate the inverse of a matrix. For a 2 by 2 matrix A, where A is equal to this matrix with the entries A, B, C, D in that order, the formula to find the determinant is AD minus BC. You can see here that we've got det of A, and that's a notation to represent the determinant. But there is another method, another way to show it. And so det of A, you could also write as a sort of straight-sided matrix with those same entries. Okay, so some things I've noticed with students I've tutored before, or students that I've been teaching, is that they get lazy with writing their matrices and they just do these lines all the time. And I have to pick them up on it. So with the straight lines, that means determinant of that matrix. That's actually the notation. And so if you want to write this matrix, you do need to do these little sort of these brackets. That's important. So when you practice, You can use this notation if you want to, but just make sure you know the difference. I'd say it's good to use that notation if you want to find the determinant. Use the straight lines. That's cool. But you just got to be really intentional with how you communicate, because slight differences in mathematics can mean something different. Okay, so here I've got an example. I want to find the determinant of B. How do I do that? Well, I'm supposed to do A times D minus B times C. So there we have it. We've got 3 times 6 minus 4 times 5. Another common mistake I see here is that kids, they do the wrong order for BODMAS. Like they do 6 minus 4 and then multiply those things. Like that's not correct. You do need to do 3 times 6 is 18 minus 4 times 5 is 20. So 18 minus 20 does give us -2. So just make sure you're doing your BODMAS correctly. Okay, we've also got another example here for C, and there's our matrix 3, 2, 6, 4. If I want the determinant of C, then I need to do AD minus BC. So let's do that. A times D is 3 times 4, minus 2 times 6 is 6 times 2. So that gives me 12 minus 12 is 0. Okay, so the determinant of C there is 0. I will say to students and teachers out there, what exactly the determinant is, I confess to not know. I've read this book called Linear Algebra Done Right, and what it does is it tries to define the determinant at the very end of all that linear algebra. So if you want to know what the determinant really is, then I think you've got to do a fair amount of study. I confess I haven't done that much to really solidly know what it is. For me, the determinant is a tool that lets me find the inverse of a matrix, and that's the degree to which I understand about it. And I'd say maybe even most teachers, that's the degree to what they understand it to be. So I guess I'd say here is the determinant, if you're a student that really seeks to understand everything about mathematics, that's fantastic, and you absolutely should. And one of my goals with learning maths is to properly understand what the determinant is, because I really like this linear algebra stuff. But you might have to wait a bit. I don't think it's the right time to go off down the rabbit hole and try and learn all of linear algebra, at least up to really understanding the determinant. I think it's probably good enough to just understand it in this to this degree for now. And if you really want to pursue that, that's something to do at university. Okay, onto a worked example. Here I've got 4 matrices, and I'm being asked to find the determinant of all of them. So I need to find the determinant of A, the determinant of B, the determinant of C, and the determinant of D, and so on. And so I'm going to do that. For the record, I can do all these by hand, and so can you. There's just a slightly longer process for the 3x3 and 4x4. So if you're interested, by all means, go and learn that. There are also some shortcuts that you can use. So, for example, I can sort of see straight away that the determinant of C is 0 because it has a row full of zeros. And so there's lots of stuff like that. If you have a triangular matrix, then the determinant is multiplying along the diagonal. So there's cool shortcuts out there to learn. And if your teacher knows some of them, why not ask them and see if they can show you? Okay, so here I'm just going to do the determinant of A the standard way that I just showed you. So if I want the determinant of A, then I need to do AD minus BC. So that's going to be 4x4 minus 2 times 3. And 4x4 is 16. 2x3 is 6. So 16 minus 6 gives me 10. The determinant of A is 10. All right, for B, I'm actually going to jump straight to D and do D. And so I can see 8 and 3. So the determinant is going to be 8x3 minus 6x4. And that gives me 8 3s are 24 and 6 4s are 24. And so that gives me the determinant of 0. What you might notice is that the first row is double the second row. And whenever we have a row that's a multiple of another in a matrix, then our determinant will come out as 0. So, lots of tricks here. You don't have to see them. You can just calculate it. That's okay. But just know that there's more going on. This is a deep subject. Okay, let's do the determinant of B and the determinant of C using our calculator. And I'll show you how to do that. There's a function that does it for us. So if we're in our CAS here, we go menu, matrix, determinant, and I've got to type in my matrix for B. So I'm going to add in that matrix. Okay, so there's our matrix. Let's put in the numbers, 6. Okay, so there's my matrix. I'm taking the determinant of that, press enter, and it turns out to be 93. Okay, and lastly, let's do the same thing, but for matrix C. Right, there's our matrix, and I predicted this would be 0, and if we compute, indeed it is. So the determinant of C is 0. All right, let's move on. Okay, so I told you that the determinant is some number that relates to a matrix, and we calculated some determinants, and you might be thinking, so what, or how do I use it? And so we use the determinant to find the inverse using this formula here. So if we have a 2x2 matrix, A is equal to A, B, C, D, and I want to find the inverse, then the formula for a 2x2 is to swap A and D, to see that have been swapped there, and then take the negative values of B and C, but leave them where they are. So you can see that B and C stay in their position, but become negative. The last step is then to multiply by the reciprocal of the determinant. So you can see that here we've got 1 on the determinant of A times that matrix that's been altered. That's the formula there. You can just plug in the values of the determinant AD minus BC, and you can write it that way if you like. But you should definitely have this in your bound reference. You should have, well, I really think you should memorize this. It's something that you'll do. If you work with matrices again, you will use these formulas. Okay, let's just read through our key takeaway, make sure we didn't miss anything. If a matrix has a non-zero determinant, then its inverse can be found. Yeah, that's important. So if the determinant comes out as 0, then we can't find an inverse. And there's the rule for a 2x2, but important to know that. We can get, so if the determinant's 0, we can't find an inverse. If it's any other number, then we can. Okay, here's a worked example. We've got the sample answer written out here for us, so let's just have a read through. We've got B and C, and we need to find the inverse matrices for B and C if they exist. If we want to work out the inverse, then we need to first calculate the determinant. So there's B, and its determinant will be 3 times 6 minus 4 times 5. And so that gives it 18 minus 20 is negative 2. Okay, so we didn't get 0, and that means that we can find an inverse. So what we do is we do 1 divided by the determinant, and then multiply that to the matrix where A and D are swapped, and B and C are made negative. So that would be 6 and 3. Notice that they have swapped, and they've made 4 negative 4 and 5 negative 5. Okay, if we compute that, then I just multiply negative a half by all the terms in there. So negative a half times 6 is negative 3. Negative a half times negative 4 gives me 2. Negative a half times negative 5 gives me 5 on 2. 2.5 is fine. And negative a half times negative 3 on 2 is, negative a half times 3 is negative 3 on 2, or negative 1.5, whatever makes you happy. Okay, so there's B inverse, and that's how we'd find it by hand. Next up, we need to find the determinant of C. Okay, so there's C, and if we do 3 times 4, that gives me 12, minus 2 times 6 is 12, 12 minus 12 is 0, and when we get a determinant of 0, we can conclude that the inverse does not exist. Okay, on to singular and non-invertible as some terminology we need to learn. Our key takeaway today is that a singular or non-invertible matrix does not have an inverse. The determinant of a singular matrix is 0. Okay, so we already talked about that fact that if the determinant is 0, then we can't find an inverse, and that's why I like non-invertible better than the language of singular. Okay, what complicates the matter even further is that an invertible matrix is also known as a non-singular matrix. So here we have we have 4 words in total. 2 of them, these 2 mean the same thing. Singular and non-invertible mean the same, and invertible and non-singular mean the same. You will see these words used in a variety of contexts, and I'd say that you probably need to know both of them. The way that I remember is that I remember that non-invertible is not non-singular. So I remember that those non-invertible and singular go together, and non-invertible is autological word. It means, you can't invert the matrix. That makes sense, whereas singular is maybe a little bit further away from that idea. So however you remember it, that's what you should do. Maybe put it in your bound reference and practice using that language when you're talking to your friends about the matrices. We've got an example here. The following matrices are non-invertible, and that means that their determinants will be 0. So you could verify this with your calculator if you wanted to. So that's a descriptor we give to matrices when we can't invert them. Okay, that's it. Here's our summary slide. We've got some key takeaways there about inverses, determinants, and some terminology, singular and non-invertible matrices. Up next, we've got binary and permutation matrices. I'll see you there. Hi, can you spot the similarities between permutations and pet minotaur? Today's lesson is on binary and permutation matrices. Let's have a look. Today we've got 2 main points. We've got binary matrices and permutation matrices. Okay, just really quickly here, binary matrices are matrices that only contain zeros and ones. So a binary matrix can be of any size, so it can have any order, right? So there's a few examples here. The identity matrix is an example of a binary matrix. Some matrices are also binary matrices, and the zero matrix is also a binary matrix. So it doesn't have to have all ones or all zeros. You can have a mix of both or not. So all those things are binary matrices. All right, on to permutation matrices. So first up, what does permutation mean? It just means swapping the order of objects. So if you've got a bike lock where you have to sort of put in your code and you turn one wheel at a time, that's called it's commonly called a combination lock, but it should be called a permutation lock because the order in which you put those numbers matters. So you've seen permutations before, for sure. Now, a permutation matrix is a matrix that we can multiply to another one that will then swap its rows or columns, depending on how we multiply it. So a permutation matrix P must be a square binary matrix. So we've got an example of P just here. So you can see what you'll notice about a permutation matrix actually is we'll only have one in any row and any column. So we won't have like a one in like two ones in a row or two ones in a column. So there's a few of those, and we'll look at all the cases of a 3x3 permutation matrix in a few slides. Here we've got two other matrices, Q and R, and I've just put 10, 20, 30, 40 in them. One is a row and one is a column. This is to illustrate that I can swap the order of these things using the permutation matrix P. So how do we do that? Well, a permutation matrix can be multiplied with another matrix Q to alter the order of its rows or columns. Okay, so here we've got an example of QP. So to change the order of the columns, P is post-multiplied to Q. It means P comes after Q. So here we've got QP, and that's going to change the order of these columns here. All right, so if we do that, then what we get out is this matrix, 40, 10, 20, 30. And all I want you to do right now is notice that it's the same numbers in a different order. All right, the next one is to change the order of the rows. P is pre-multiplied to Q. So actually, in this case, I've used R. It's not really important what we call those matrices. So just know that here, I'm going to shift the order of these rows here in matrix R. So here you can see I've got the same P times this column matrix R, and it's in order, ascending order 10, 20, 30, 40, and after we do the multiplication, see that it goes into a different order, 20, 30, 40, 10. Okay, let's push forward. Okay, a little bit more on permutation matrices. How can we read them? So first things first, some notation. A permutation matrix P has elements P, I, J. That's just referring to the positions of the elements inside matrix P. To change the order of the columns, P is post-multiplied to Q. So here we can see QP, so that's P being post-multiplied. And what this will do is we'll shift columns. So a 1 in position Pij will make column I become column J in the resulting matrix QP. So to give a concrete example for this, a 1 in position 1, 2, so row 1, column 2, will make column 1 become column 2. Let's verify that this works for this matrix here. So here's our target matrix to shuffle the columns of. And let's look at all these ones. So the top one here, that's in position 1, 2. So column 1 should become column 2. So column 1 is here, and you can see it's become column 2 in the resulting matrix. Let's check all the other ones to make sure that this still works. So this one here is in row 2, column 3. So column 2 should move to column 3. So column 2 is here, and you can see it's moved to column 3. All right, two more. This one here is in position 3, 4, so row 3, column 4. So it means that column 3 will move to column 4. So 3, 7, 11 is now in column 4. Okay, lastly, hopefully this one's going to work. So it's in position 4, 1, so row 4, column 1. So it should move column 4 to column 1. And that's exactly what we see. 4, 8, 12 has moved to the front. Okay, let's clean the diagram up, and then we'll look at permuting rows. And actually, this is sort of backwards, so we need to pay close attention. Okay, onto rows. So to change the order of the rows, P is pre-multiplied to Q. And actually, I've used R here. It doesn't really matter what we call that matrix to be permuted. So a 1 in position Pij will make row J become row I in PQ. So there's actually the other way around. So a 1 in position P1, 2, so row 1, column 2, will make row 2 become column 1. It's sort of going the other way here. So you just got to pay attention and make some notes so that you get this right. on the day in your exam or in your SAC. Okay, so let's have a look. Now here is the same permutation matrix, and we've got a position in row 1, column 2. So that should move row 2 to row 1. So row 2 is here, and indeed it has been moved to row 1. Let's keep going here. This is in position row 2, column 3. So it should move row 3 to row 2. And it has. Good, that's checking out. Okay, this one here is in position row 3, column 4. So it should move row 4 to row 3. And it has. And lastly, this one is in row 4, column 1. So it should move row 1 to row 4. So row 1 has been moved to row 4. Okay, looks like it checks out. Okay, here's a worked example. We've got a matrix Q and a permutation matrix P, and we're going to calculate QP by hand. So we're just going to do the calculations. And so I've actually prepared just that part of the matrix there. So I'm going to make our shell. Now we've got a 3 by 4 matrix and a 4 by 4 matrix. So we should get a 3 by 4. So I'm going to make enough space to do that. Okay, and let's fill it in. So I'm just going to do, you can think about like which one should go where based on these ones. I'm actually going to do the computations so you can see it in action. So here, my first position, I've got to do row 1 and column 1. So I can sort of see that as I move along the row and down the column, I'm timesing by 0 a lot. If I times by 0, I just lose that number. So sort of like 1, 2, 3, and 4 is the only one that matches up with the 1. So it returns a 4. Okay, moving along. Now I need to do this position here, which is row 1, column 2. So I need to look at row 1, column 2. And I can see that the 1's matching up with the 1. So it's going to return a 1. And now I'm on to the next one, which is in row 1, column 3. So I need to look at row 1, column 3. And I can see that the 1's in the second position and the 2's in the second position. And that's how they're going to meet when they multiply. So I'm going to get 1 times 2 is 2. And last one, I need to do position 1, 4. So I look at row 1 again and column 4. And that will give me, I can see that the 1's in the third position, and so is the 3. So it's going to return the 3. All right, cool. So I've got 4, 1, 2, 3. So maybe you can already see that column 4 has moved to position 1. Column 3 has moved to position 4. Column 2 has moved to position 3. And column 1 has moved to position 2. Right? So we can already see how those columns have shifted, even though we haven't worked out all of the columns yet. Okay, let's clean up the diagram and I'll swap colors so we can see the next one. I'm going to do the next one in red. So now I'm working in row 2 and I need to multiply row 2 with column 1 to get that first position. And I can see the 1 is lining up with the 8. So there's the 8. And then the next position is row 2, column 2. And I can see the 1 is going to line up with the 5. So I'm going to get 5. And then the next one is row 2, column 3. And I can see the 6 and the 1 are going to be in the same position. So I get a 6. And finally, row 2, column 4 lines up with the 7. Okay, so again, you can already see that the columns are lining up. And you could compute again, but I don't think we need to. So I'm just going to pop in the rest. And 1, 5, 9, and 2, 6, 10, and 3, 7, 11. Okay, so we did it by hand. Hopefully that shows you how the permutation matrix works to shift the columns. Okay, so we looked at doing a permutation of columns by hand, and now we're going to do a permutation of rows by hand. So here I've got matrix R and P, and I'm going to do PR, which will swap the rows. So I've got a 4 by 4 matrix and a 4 by 3 matrix. So I think my resulting matrix should be a 4 by 3. Okay, so let's get going. I need to work out the position in row 1, column 1. So I need to take the dot product of row 1 and column 1. And we can see that the ones lining up with the 4 as we move across the row and down the column. So it's going to return 4. So I'll put that in. And then I need the next number, which is in row 1, column 2. So let's look at row 1, column 2. And the one's lining up with the 5. And so we can already see we're taking that row, and it looks like it's shifting up to row 1, I should say. So Yep, that gives me back 5. And if I go for row 1, column 3, and I can see the 1 is lining up with the 6. So it will return 6 when I multiply those two things. And so there it is. So I get 4, 5, 6. Excellent. So now what you can sort of tell is like I only need to work out that first number to see where the row is going to go. So I'm going to do that. Oh, well, first let's clean up the diagram. Okay, I'll do this row 2 in red. So for this position here, I need to look at row 2, column 1. So there's row 2, column 1. And the third value is lining up with the 7. So I'll put a 7 there, because that's going to work out. And let's do row 2, column 2, which we can see is 8. So 0 times 2, 0 times 5, 1 times 8 gives me back 8. And I can sort of see I'm taking 7, 8, 9, so I don't even really need to do it again. I can see that it's just going to be 9. And let's look at the next one. Okay, let's do it in green. So in my next row, I'm actually going to have a 4 by 3 matrix, so I might need to extend this in just a moment. We'll get there in a bit. So row 3, column 1, looks like my 1's in the 4th position, so I'll times that with the 10, and I get the 10 back. All right, and then moving to the next one, row 3, column 2 is going to be row 3, column 2 gives me back an 11. Okay, and so you can see I'm taking this row now, so I can just pop in the 12. Just going to extend that matrix down. Okay, matrix is cleaned up, so let's go. We need row 1, column 1. So row 1, column 1. Oh, look, 1's in the 1st position, so we're going to return that 1st position. That's a 1. And to get row 1, column 2, I need row 1, column 2, and the 1's lining up with the 2. So we'll put a 2 in there. And finally, we've got row 1, column 3, which is a 3. Excellent. So we've got our final matrix there. Hopefully seeing it done by hand helps you understand how the permutation matrix is working to shuffle the rows and previously the columns. So as permutation matrices need to be square matrices, a logical question to ask is, well, how many are there, or how many can there be? And it turns out there's only 6 possible 3 by 3 permutations. So here they are. I've drawn them all out. And so you'll notice this first one's the identity. It actually doesn't permute anything, but it still classes a permutation matrix. It just moves column 1 to column 1 and so on. It sort of just preserves the matrix, gives us back what we needed. But then how could you find the others? Well, you sort of, you keep your top row the same, and then you switch the bottom two. So I just sort of swap these two to get this matrix. Hopefully you can see that. And then you're like, okay, well, I put that 1, 0, 0 in the top. Well, what if I move the second row to the 1st position? Then I've got 2 options. I can have that 1, 0, 0 there and a 0, 0, 1 there, or I could swap them. And you'll see that that's this option there. So I've counted 4 of them, and I think I've got 1 option left. I can have that 0, 0, 1, that swap's actually occurred there, and I've got 0, 0, 1 in the top row here, and I've got 1, 0, 0 in the second, and the third in that other matrix. So hopefully you can see how I've generated every type of permutation matrix there for a 3 by 3. You might like to try the exercise of finding all the 4 by 4 permutation matrices. And while we're here, we might as well just look at the 2 by 2 permutation matrices that we can have. And actually, not very interesting, we can have the identity matrix, which doesn't do anything, or we can have 0, 1, 1, 0. And what that does is just switches the rows or switches the columns. And that's it. Cool. Okay, here's our mega question activity. The matrix product shown shuffles the letters in the word permutation to pet minotaur. It's an anagram. Which change to the permutation matrix will ensure the phrase pet minotaur is preserved? So here we've got permutation times this massive 11 by 11 matrix, and it should spit out pet minotaur. Can you make a change so that it still does spit out pet minotaur? Okay, the answer here is to swap rows 6 and 8. So if you used your CAS calculator, hopefully you see that that works. And all this is doing is swapping the t's. So actually, if this was the first t and the second t, then they're actually going the opposite positions after we make that row change. This here is a couple of pictures of minotaurs. I was trying to find a picture. This one was some free image that we could find. But this one here is generated by an AI. At the moment, AI is blowing up all over YouTube, and I've been playing around with it. So, I just asked for a cute picture of a pet minotaur, and that's what I got. So, it looks a little weird, but it's pretty good for a computer. In summary, here's some stuff about permutation matrices. I think it'd be cool to put the post and pre-multiplication for changing rows and columns in your bound reference so that you've got something to look at during your exam. Okay, I'll see you next time. All right, if Collingwood defeated Geelong, who defeated Brisbane, who defeated Collingwood, who's the best? I'll let you argue amongst yourselves. Welcome to the lesson on communication and dominance matrices. Today we're looking at communication matrices and dominance matrices. They're pretty similar, so let's have a look. Okay, our key takeaway today about communication matrices is that a communication matrix represents the connections in a communication system. So this could be like computers talking to each other, or telephone communications, or just connections on social media. A communication matrix can be undirected or directed. So let's have a look here. This first one is an undirected communication matrix because the edges don't point in any direction. So in comparison, or in contrast, the directed communication matrix does have arrows pointing along the edges. So for example, this one here shows that B can communicate with C directly, but not the other way around. So C doesn't talk to B. Each of these has an associated matrix. And so in an undirected communication matrix, that's going to be symmetrical about the diagonal. If B talks to A, then A can talk to B. Whereas here, we can see that B can talk to C. So B talks to C. So row B can talk to column C, but C cannot talk to B. So there's a 0 there, right? I think it's fairly obvious that a 1 represents there's communication and 0 represents that there isn't. Okay, with communication matrices, we have this concept of one-step or two-step communication. So one-step communication would be sort of direct communication. So for example, vertex B talks directly to vertex C. And that's indicated here in matrix C. So we can see B is talking to C. So we read row first, column second. And we see there's a 1 there because B is talking to C. We can also have two-step communication. So you can think about, well, if B tells a secret to C, and then C tells that secret to D, then that secret has traveled from B to D, but not directly. So it's traveled through another party. And that's called a two-step communication. So we can get all the two-step communications by squaring the first one-step matrix. So here, C squared, this tells me the two-step communications. I've tried to highlight them in the matrix here. So we've got a 1 here from A to A. Okay, so that's from this pink loop here, going from A to B and then back from B to A. This one is actually a redundant communication link because it's sort of like you tell a secret to someone and they immediately tell it back to you, and you go, oh, "Yeah, I just told you that," right? Everyone sort of had that conversation before, like when someone tells you a joke that you told them. So that is represented here. That's a redundant communication link because the information didn't really travel somewhere new, right? And so we can see this is different to this one highlighted here in blue, which is B communicating with D via C. So here B communicates to C and then to D through C. So there you go. That's two-step communication links and redundant communication links. All right, in general maths, we want to look at total communication links, which we're going to define as C plus C squared. So if we add these two matrices together, we're going to get all of the one-step communications from C and then add all of the two-step communications in C squared. So here we have T equals C plus C squared, and these are the matrices from before. And we can see that if we add them together, then let's just look at the first row. So adding these rows, we're going to get 0 plus 1 is 1, and 1 plus 0 is 1, and 0 plus 1 is 1, and 0 plus 0 is 0. Okay, and so we can continue adding in that fashion, and this gives us our matrix T. Okay, here's a worked example. 4 towns communicate via mail as shown in the network diagram. Find the total number of one-step and two-step communications between towns. Okay, to do this, I've got 4 vertices, so I'm going to need a 4x4 matrix. So I'm going to draw that and call it C. Okay, there's my shell. And let's go through and look at the directed communication links. So important here to go row first and then column. So can this row talk to this column? So first off, can A talk directly to A? No, it can't. And so we put a 0. Can A talk to B? Again, no, it can't. But it can talk to C. It can't talk directly to D. So that row is done. A quick way of doing this is to say, okay, I'm on to row B now. And who can B talk to directly? Well, B talks directly to A, and nobody else. So I'm just going to put 1 for A and 0s everywhere else. And now I'll go to C. Who can C talk to? Well, it looks like it talks directly to B and D. So I'm going to put 1s in columns B and D. And lastly, who can D talk to? Well, D looks like it talks directly to B, and that's it. So we found the one-step communication links. And so we're asked to find the total number. So I need C and C squared, and then I need to add them. So I'm going to find C squared, and I'm going to do that by hand. So I've got C times C. So I'm just copying that matrix in. Okay, I've got my matrices now, and if I do a 4x4 times a 4x4 matrix, I will get a 4x4 matrix. So let's just make that shell there. Okay, so now like I can do these multiplications. You could do it with the CAS if you wanted. I'm just gonna run it quickly. So if I want this first position, then I need to look at row 1, column 1, and I can see that none of the 0s and 1s are lining up, and so I can't get a 1. So that's going to be a 0. Alternatively, you could ask yourself the same questions from the network diagram. You could say, well, what can A talk to in 2 steps? And you can see A can talk to B along this path here. And so there should be a 1 in that AB column. So let's see that we get that now. So here we're going to go row 1 times column 2. And we can see that the 1 is lining up. Okay, and that's so it's sort of saying like, well, A can talk to C and C can talk to B. So those two things to combine to give A talking to B, right? So that comes out as a 1. Awesome. Let's keep going. So I need row 1, column 3. So row 1, column 3 is going to give me none of them line up, so it's a 0. And row 1, column 4 gives me 0, 0, 1. Oh, yep. So the 1s are going to line up there, and I get a 1. And we can see that 2-step communication that A is talking to C, who is talking to D. So that's 2 steps away from A. Okay, if we keep going, then we'll get the C squared matrix. So I'm just going to do that now. Okay, so there's our C squared matrix. Very good. Now, if we want the total number of 1-step and 2-step communication between towns, then I'll do C plus C squared. Okay, so I've just moved up here to the top right. So I'm going to write those matrices next to each other so I can see them. So here's C, and here's C squared. Okay, there's the 2 matrices, and if I add them together, it shouldn't take too long. I can see 0, 0, 1, 0 plus 0, 1, 0, 1 should give me 0, 1, 1, 1. And then adding the second row should give me 1, 0, 1, 0. Adding the third row should give me 1, 2, 0, 1. And adding the fourth row should give me 1, 1, 0, 0. Okay, there we go. Okay, onto dominance matrices. Our key takeaway today is that a dominance matrix holds the information of the outcomes of competition. The 1s and 0s in a dominance matrix represent wins and losses respectively. We can't have draws in one of these matrices. Dominance matrices are always directed because somebody has to defeat someone else in competition. Okay, so here's our example of Annabella, Bradley, and Chris playing a table tennis competition. We've got a network diagram and an associated matrix here. So let's have a look at that. So we can see that Annabella defeats Bradley, and Bradley defeats Chris, and Annabella defeats Chris as well. Okay, so we can see that here in the matrix. So Annabella defeats Bradley and defeats Chris. We can see that Brad defeats Chris, and Chris doesn't defeat anyone, so there's 0s. So if we add up the numbers in each of these rows, we get a dominance score. In this case, 1-step dominance score. And so adding them, we get 2 for Annabella, we get 1 for Bradley, and Chris gets a 0. And so that will be their ranks. So in the ascending order of dominance score, we can see that Chris is the worst table tennis player, Bradley is the middle, and Annabella is the best. Okay, on to 2-step dominance. You probably intuitively already understand this. So let's talk about 3 teams playing each other in any sport or any competition. If A defeats B and B defeats C, what do you suspect about what will happen when A and C play? You probably suspect that A will defeat C because they beat B who beat them. Okay, so that's the idea of 2-step dominance. Even if A hasn't played C directly, we still suspect that they are better than C because they beat someone who beat them. All right, so looking at the text on our screen, let's see if we glean anything new from these points. So the first point says, if the outcome of a competition or tournament is not obvious from one-step dominance, then two-step dominance can be evaluated. So if we're not sure who's the best out of a few games, we can look to two-step dominance to get an understanding of who might actually be the best player, even if everyone hasn't played yet. Okay, two-step dominance occurs when one competitor has a dominance over a second competitor, and the second competitor has a dominance over a third competitor. So A defeats B, who defeats C. All right, squaring a dominance matrix D will generate a two-step dominance matrix D squared. So here we've got an example that I've extended. Annabella, Brad, and Chris start a new table tennis tournament with their friend Dominic. The outcomes are shown in the network diagram below. The one-step dominance is calculated, and the two-step dominance is obtained by squaring the one-step dominance matrix. So let's evaluate here. Here's our competition. We can see that Dominic's defeating A and C, and that's represented in the matrix and so on. So that's our matrix that represents this tournament. And here D squared shows the two-step dominance. So we can see that Dominic has two-step dominances over B and one two-step dominance over C. Let's see where that is. So you can see here that Dominic defeats A and A defeats B, right? So that's one of the two-step dominances that Dominic has over Brad. And Dominic also defeats Chris, who defeated Brad in this tournament. So there's the two-step dominances over Brad. He also has a one-step dominance over Chris, and we can see that here. So Dominic defeats Annabella, who defeats Chris, and so that's the two-step dominance that Dominic has over Chris. Okay, so all of that information is encoded in that matrix, and if we want the total dominance, we can add those two. Okay, so that brings us to this slide on total dominance. To find the total dominance T, add the one-step and two-step dominance matrices, just like we did with one and two-step communication matrices. This is really the same idea. Okay, there it is there. So here's our matrices from before, just the same examples. If we add them together, then we get this matrix. And if we add up those rows, this gives us a dominance score. So Annabella gets 4, Brad gets 3, Chris gets 2, and Dom gets 5, which shows that Dom is the most dominant player. This was not immediately obvious from the one step, because if we calculate the dominance scores here in this matrix D, you can see Annabella gets a score of 2, Brad gets a score of 1, Chris gets a score of 1, and Dominic gets a score of 2. So from the one step, it's not clear that Dominic is better than Annabella or that Brad is better than Chris, but we can see that in the total dominance matrix. So there's Brad, there's Chris, and there's Annabella. Okay, here's our summary slide. You can see that the communication and dominance matrices are really similar formulas. I mean, they're essentially the same. And just the other thing to notice is that redundant communication links appear along the diagonal of communication matrix. All right, up next we've got transition matrices. I'll see you there. Did you know that the Earth's population is now at 8 billion people? It's a lot of people. And we expect that it will reach 10.4 billion by the year 2100. So that's less than 80 years away to get another 2.4 billion people. I mean, it's so many people. How do we predict this, though? Today's lesson is about modeling population migration or growth. So let's jump in and have a look at how we can do this with some mathematics. Welcome to an introduction to transition matrices. From here on out, most of the questions are about transition matrices. So I wouldn't move on from this lesson until you feel like you know what's going on. Okay, 3 main points today. We've got transition matrix, a state matrix and recurrence relation, and a Leslie matrix, which is sort of like an application of a transition matrix. Let's jump in and have a look. Okay, transition matrix. Our key takeaway today is that a transition matrix T, that's this guy down here, is a square matrix that represents changes to states within a system. A common use for transition matrices is to model population change or population migration. So in this case, I'm modeling a migration, and we can see 2 cities here, Melbourne and Adelaide, and moving between them. So just looking at this diagram, I'm going to point out what each of the arrows represents. So here we can see that this arrow is pointing back to Melbourne, and that's representing 95% of Melburnians staying in Melbourne every year. This arrow here points out of Melbourne, and that's the remaining 5% of people that will move to Adelaide. Okay, we've also got 2 arrows coming here out of Adelaide. And what do they represent? Well, this one here pointing back to Adelaide is the 90% of people from Adelaide that will stay there. And this one here, the 0.1, is the 10% of people from Adelaide that will move to Melbourne. Okay, so that's the diagram. Let's just clean it up a bit. Okay, what I want you to notice is that this information can be encoded into a matrix. So that's the matrix here, T. What's different about this transition matrix is we're going to read it column first. And that's different to almost everything else that we've been doing so far. Even in the last lesson, we were doing row, then column. This time, we're going to look column to row. So here, in this position here, we've got a 0.95. This 0.95 represents the Melburnians staying in Melbourne. Okay, so from Melbourne to Melbourne. And just underneath it, we've got people from Melbourne moving to Adelaide. And that checks out with the diagram here. Okay, so from Melbourne to Adelaide, looking down the column and then across the row. All right, the next one, we've got this position here. That's from Adelaide to Melbourne, and that's 10%, just like in the diagram. And the last one, Adelaide to Adelaide, is 0.9. What you should notice here is that we've got 0.95 and 0.05, and they line up and they add to 1. So the column in a transition matrix must add to 1, okay? And that's here as well. And that's because 100% of the people in Melbourne need to either stay there or move somewhere else. So in this model, we're not allowing for the population to change or grow. So we're assuming sort of like nobody's born and nobody dies. And that's not a perfect model, of course, by any means, but it is still a useful model to look at. So we're looking at a fixed population moving between two cities. Okay, let's move on. Okay, here's an example. Let P be equal to the column matrix where we've got a 5 and a 1. This represents the population in millions of Melbourne and Adelaide. Actually, just so you know, I'm putting Melbourne in the top and Adelaide in the bottom there. All right, and this is the population in 2023. We're going to let T be that transition matrix from the last slide. Yep, so that's working out fine. So this represents the proportions of population moving between these cities, just like we saw in the last slide. The matrix product TP will yield a new matrix containing the population in millions of Melbourne and Adelaide in 2024. Okay, so that 5 in the matrix really represents 5 million, and the 1 represents 1 million. Okay, now if we calculate TP, so we times that transition matrix to this value here, then we're going to get this new matrix which represents the population the next year. So we can see Melbourne's population has declined to 4.85 and Adelaide's has increased to 1.15 million. Okay, so just take a moment, maybe even do that calculation by hand to see why we get 4.85 in Melbourne. That calculation would be from row 1, column 1. And so if you times row 1, you take 0.95 of 5 million, so 95% of 5 million, and then you add 10% of 1 million. And that ends up being 4.85. Likewise, if you want to see how the 1.15 million is calculated, that's in row 2, column 1. So you multiply row 2 with column 1. So you get 5% of 5 million plus 90% of 1 million. You add those together and you get 1.15. So that's how the transition matrix is working to shift those proportions between the cities. Here's a worked example. We've got the manager of a fruit farm organizes 45 employees into 2 groups, collectors and sorters. The collectors gather fruit while the sorters dispose of the produce not fit for sale. On Monday, the manager allocated 40 employees as collectors and 5 employees as sorters. On Tuesday, the manager decides that 80% of the collectors should become sorters. Define a transition matrix T and create a matrix product to determine the number of collectors and sorters on Tuesday. Okay, so what we want to do here is maybe we can draw a transition diagram first. Maybe that will help us. So we've got collectors and we've got sorters. And it's Monday now, but tomorrow we want to put 80% of collectors over to sorters. Okay. And I think that means that 20% have to stay as collectors. So you can write 8% or 0.8, it doesn't really matter. And then it says that that's the only thing that happens. So I have to assume that all the sorters remain sorters. So this is 1.0 or 100%. And that means that 0% move from sorters to collectors. Okay, if I want to represent these things, then I think I could put, like, let's say P is the population of collectors and sorters, and I could say, well, that's going to start at 40. We had 40 collectors, and we had 5 sorters. I find it easy to think about what the final answer should be. So we're going to do TP, and that's going to be some transition matrix here times that 40 and 5. And here, my final matrix, that should be what I get on Tuesday. So just thinking, I'm supposed to get 80% of collectors becoming sorters. So that means 20% of these guys need to return to being collectors. So I think I want to times, to get this position, I would multiply this row and this column. So I want to get 20% of 40, so that's going to be 0.2. And then I don't want to take any of the sorters to be collectors. So that's going to be a 0 there. Okay, if I work that out, 0.2 times 40, that's going to be 8, I think. And then 0 plus 5 is going to be 0. So I'm just left with 8 in that position. Okay, let's find the next row of that transition matrix. Well, I'm supposed to move 80% of the collectors to the sorters. So I want this position here, which is row 2, column 1. So if I times row 2 with column 1, then I need to do 80% times 40, and then I need to do, 100% of the sorters returning. So that gives me 0.8 times 40 gives me 32. And then add 5, I'm going to get 37. And so what we can see is here the population hasn't changed. I had 45 people in total here, and I have 45 people in total here. So that's all checking out. Okay, so just reading back, what did the question want me to do? Find the number of collectors and sorters on Tuesday. Well, that's 8 collectors on Tuesday. Maybe I should say 8 collectors and 37 sorters. Okay, and I was supposed to define T. So I found T, although, I sort of did it in the middle of everything, but I have found T. It's 0.2, 0, 0.8, and 1. Okay, I don't think about the transition matrix in isolation. I think about it, how will it multiply to this population matrix? And what numbers will it give me? I think that's the best way to think about it. Turns out we don't just want to calculate one shift in population, but many shifts. And we can do this recursively. So we've got a formula here where S0 is the initial state matrix, and the next one, Sn plus 1, will be transition times the previous population. So if you want S1, then you need to do T times S0. Okay, let's just have a look at this key takeaway here. So it says a state matrix S contains the information of a system at a point in time. So the population of Melbourne in 2023. When modeling populations with transition matrices, the state matrices usually contain the populations after a number of years. So what that means is I could have S10, and that state matrix means the population after 10 years, or 10 transitions. Okay, so here's an example. Looks like I'm back to my Melbourne-Adelaide one. So that's the one we saw before. And S0 was 5.1, and I wanted S1 to be 4.84 times 1.15. So I did that exact calculation before. I just used P's instead of this S0, S1 notation. So that's really all that's changed. Okay, so I've got S0 and S1, and they represent the population in millions of Melbourne and Adelaide in 2022 and 2023. T is the transition matrix that allows us to calculate S1 from S0. And you can see that we do this by S1 is equal to T times S0, which gives us T here times the original population, and that gives us the population in the next year. The point here is we could do this again and again and again and again and again to get S2, S3, S4, S5, and S6, and so on. Okay, now the recursive relationship is good, but we can actually generate an equation to find the nth transition. So here we've got a state matrix Sn can be calculated by repeatedly multiplying the initial state matrix S0 by the transition matrix T. So here we've got S0 is the initial state matrix, usually initial population. And to find Sn, so some nth transition, or maybe like S10, say, then we do T to the power of that n, so T10, T to the power of 10 times the initial state matrix. So what does it look like in practice? If we want to find the fifth state matrix, then we need S5. And this will be t to the power of 5 times S0. So all we need is t and the initial state matrix, and we can quickly calculate any number of transitions. I've got a calculator here to show you how to do this, but if we take t and raise it to the power of 5 and multiply by the initial population of 5 million and 1 million in Melbourne and Adelaide respectively, then we should get this number here, 4.44371 million in Melbourne and 1.55629 million in Adelaide. So doing that by hand would be very cumbersome. So this is why a calculator is good. So let's pull up the calculator and see how to do it. Okay, so I put the matrices in. You can see I've raised t to the power of 5 here. And if we press execute, then we get our number here. And you can see it's calculated significantly more decimal places there, just because that's how this calculator's set. And that's fine. So there you go. Okay, I've got some maths here to show you how we actually derived this rule from this rule. And so there's some maths here. So let's have a look. If we start just generating the figures, we can sort of see by continuing the pattern how this formula should come out. So we've got S0 is the initial state matrix, then S1 is equal to T times S0. And if we can find S2, well, that's supposed to be T times S1. But we know the expression for S1, that's T times S0. So what you should see is instead of S1, we've replaced it with an expression in terms of the initial matrix, S0. Okay, then you've got T times S0, and it turns out it doesn't matter what order you times these matrices. So we can do T times T to give T squared. Okay, so we've got T squared, S0 gives us the second term. Likewise, S3 is equal to T times S2. But we know that S2 is T squared S0 from the previous example, and we plug that in here instead of S2. And so then we have an expression in terms of the initial matrix S0. So we have T times T squared times S0, which gives us T cubed times S0. If we continue that pattern, we get down to Sn, the nth state matrix, and that would be T times the one before it, S of n minus 1, or Sn minus 1. Now what you do is you just sort of look at the pattern here. It seems that this number is always one less than the one over here. And so if this is n, then this power must be n minus 1. You might remember from index laws that t to the power of n minus 1 should be t to the power of n. And that's where we get our final result there, that Sn is equal to t to the power of n times S0. Okay, so a bit of algebra there to get from here to here. But hopefully that makes you feel like these two things are related, because they are. Okay, so here's another example we're going to try. We've got the same transition matrix about moving from Melbourne to Adelaide, and we've got the same initial state matrix of 5 million in Melbourne and 1 million in Adelaide. Let's read the example and see if we can do it. S0 represents the population in millions of Melbourne and Adelaide in 2022 and 2023. T is the transition matrix describing the population migration between the two cities. Find the state matrix that represents the population of the cities after 10 years. Okay, so what's it asking for? It really wants S10, so there'll be 10 transitions after S0, and this will be given by T to the power of 10 times S0. Okay, well, I think we've actually got all those things, so let's plug them in. So this should be this matrix here, 0.95, 0.05, 0.1, and 0.9 to the power of 10, times that matrix with a 5 and a 1 in it. Okay, let's do that on our CAS, because by hand that would be very, very difficult to do. Okay, so here's our calculation we need to do, and let's go. Let's do it. And we get 4.197, say. Let's just do it to 3 decimal places. That's fine, I think. So this is 4.197 and 1.803. Okay, so I just chose some decimal places there. You could take all of them if you wanted to, it's fine. Usually the question will direct you how many decimal places it wants. Okay, so we found S10, that's good. I should say, before I just said it would be very, very difficult to do by hand. And that's sort of true. There is a way to work this out by hand a little bit easier, and it's I'm not actually sure how easy it would be by doing it without actually jumping in, but it's called diagonalizing a matrix. And that method lets us raise matrices to the power sort of more easily by hand. So, that's something that we could actually do if we did want to do this by hand. And that is the method that we would probably follow, because running those calculations, raising this matrix to the power of 10 is certainly difficult, but we can sort of get around it in a clever way. Anyway, we don't need to worry about that. So long as you can find S10, you're all good for today. Okay, let's look at an example called a Leslie matrix, which is a type of transition matrix that we can use to evaluate species, population, growth or decay. So a Leslie matrix L is an application of transition matrices that models the growth of the female population of a species. That's an important distinction here, that a Leslie matrix only monitors the female population. Okay, a Leslie matrix stores the following variables. Fn is fecundity or fertility rate of n-year-olds, and Pn is the average survival rate of n-year-olds. Okay, so let's look at these things here to try and decipher what this matrix stores. First off, S0, that's still the initial population. So I've sort of said here, X, Y, Z, that's the population of 0-year-olds, 1-year-olds, and 2-year-olds, or 0 to 1-year-olds, 1 to 2-year-olds, and 2 to 3-year-olds. Okay, so yeah, that's sort of what those different categories mean. And then along the top row, we have the fertility. And fertility here doesn't mean all the population of this age group that can make offspring. It's the ones that do. So here, this is sort of the average birth rate we expect from this particular age group. So this position here, F0, is the average number of females born to all the females less than 1-year-old. F1 is the average number of females born to all of the 1-year-old females. And F2 is the average number of females born to all the 2-year-old females. P0 is the average survival rate of females that are less than 1-year-old, and P1 is the average survival rate of females that are 1 year old. So in a population of animals, we don't expect all of them to survive. And so in this case, these values here sort of tell us how many of that species makes it to the next state. Okay, I think that's everything on that slide, so let's move forward. I wanted to show you a general Leslie matrix. So here we can see one, and that Leslie matrix can sort of be as large as you want it to. If you're going to use it to model a population, it sort of needs to be as large as how old the species lives. So if you're going to do it for humans, that matrix might actually need to be like 100 by 100 matrix. The other thing to note here is like what's going on with these dots. This is called an ellipsis. It means this pattern continues. So what I'm trying to show you here is F0, F1, F2, F3, and the next one will be F4, and the next one will be F5, and so on up to some nth value. Okay, likewise here we've got the survival rate of the 0-year-olds, the 1-year-olds, the 2-year-olds, and here the n-1-year-olds. Okay, there's zeros everywhere else in that matrix. So yeah, that's the general one. Okay, let's investigate a recursion relation for Leslie matrices. So a changing population of females can be modeled using a Leslie matrix and a recursion relation. So what this will do, we'll have an initial state matrix, S0. Okay, and over here in our Huntsman example, that's this one. And that contains the initial population of spiders. You can see in this example, we've got 0-year-olds, 1-year-olds, and 2-year-olds. Okay, so they're the different age brackets of Huntsman. And in the Leslie matrix, I've got stuff about their fertility or fecundity rates and their survival rates down this sort of off diagonal. So, this is really quite similar to what you've done with the transition matrices. It's the same recursion relation, but we've swapped L for T. So in a transition matrix, the columns add to 1. That's not true of a Leslie matrix. In fact, you can see that pretty plainly from looking at this one. However, doing the recursion works in much the same way. We're still, the Leslie matrix is going to make a transform on the state, and we're going to get the next state after that. That's Sn plus 1. Okay, so let's look at this example of Huntsman's. Huntsman's live for about 2 years, and that's why I've got these 3 age brackets. The fertility and survival rates in a population were monitored. The Leslie matrix below can be used to model the population change. So you can see that if you just sort of like scan ahead, I'm calculating 2 years. I'm calculating the population of Huntsman's after 2 years. So let's look at how I do that. To make this calculation, if I want S1, I need to compute L times S0. And so here I've got L times my initial state matrix. So we can see initially there were 500 0-year-old huntsmen or baby huntsmen. There are 100 adolescent or juvenile or middle-aged huntsmen at 1-year-old, and I've got 10 adult huntsmen. In this Leslie matrix, what you can see is the fecundity rate. So I can see that 0.1, 20, and 30. And that tells me how much the corresponding age groups reproduce. So on average, we expect, I'd say 20 babe huntsmen to be born to the to each of the 1-year-old huntsmen. So eventually when you do the product of those two things, you're going to get 20 times 100. So maybe I'll draw out what that would be. You can just do this on the calculator. So if I'm going to compute these two things, I've got to do the first row with the first column. So that's going to be 0.1 times 500 plus 20 times 100 plus 30 times 10. To get the next entry in row 2, column 1, I need to multiply row 2, column 1. So I get 0.02 times 500. I get 0 times 100 plus 0 times 10. And for the final entry in S1, we need to do row 3 by column 1. So that's 0 times 500 plus 0.05 times 100 plus 0 times 10. Okay, so lots of calculations there, although it is important to sometimes do it by hand. I think if I work out those numbers, I should get this. So 0.1 times 500, that's going to be 50. 20 times 100 is going to be 2,000. And 30 times 10 is going to be 300. So you can see that's going to give me 2,350 when I add them together. So it has worked. My next entry is 0.02 times 500. So that's 2% of 500. I think that's going to be 10 plus 0 plus 0. So you can see that one's worked out too. And finally, I've got 0 times 500 plus 0.05 times 100. That's going to be 5. And then 0 times, that's 0 plus 5 plus 0. And so I get my answer there. I get 2,350, 10, and 5. Okay, so I've calculated S1. Looks good. You could just use the CAS if you want to do it fast. That's great. Okay, but I think I'm going to S2, so I have to do this again. So if I want S2, I do the Leslie matrix times S1. And so there's that computation there. And if you throw that in the CAS, you should get this answer. So we get 585 0-year-olds, 47 1-year-olds, and half a 2-year-old. Now, if I was to stop there, if I wanted to find the population after 2 years, I would round up to the nearest whole number. So it's a model of my population. I can't have half a 2-year-old spider. And so in this case, I'm going to round up, right? That's just what my model predicts. So sometimes I'd be giving my answer like this, 47 and 1, if the question prompted me to round to the nearest whole number, which is what I've seen from most of the questions so far. I would like to say, if you're going to find S3, you wouldn't use this num in your calculation. So you don't do any rounding until the final step, right? So just something to be aware of. Okay, let's move on. Okay, so we looked at using recursion. So if I wanted S1, I had to use S0. If I wanted S3, I had to use S2, and so on. So I can do one step at a time. But just like in transition matrices, I can skip steps. So if I wanted to find some higher value of n, I can use this formula where I do Sn is equal to L to the power of n times S0. So I'm just going to raise the L to that power, whichever step I want to go to. So let's have a look at this one here. Huntsman spiders live for about 2 years. The fertility and survival rates in a population were monitored. The Leslie matrix below has been used to find the population of female spiders after 4 years. Okay, so I've done this calculation for you. If I want S4, then what I can do is write L to the power of 4 times S0. So L is here, so I raise that matrix to the power of 4. and then multiply by the initial state matrix. If you put this in the calculator, then you'll get S4 is these numbers here. Usually you'd be prompted to round your answer to the nearest whole number, and if we did that, what we'd be predicting would be 406 baby spiders, 20 one-year-old spiders, and 1 2-year-old spider. Okay. If I wanted to find S5 though, and I was using a recursion relation, I wouldn't round. Remember, I only round for the final step when I'm asked for that final approximation to what the population is. Here's another worked example. The ruby-throated hummingbird lives for at most 4 years. Scientists are tracking a flourishing population in Mexico and have created a Leslie matrix to model their population growth. The Leslie matrix and initial state matrix are L and S naught presented there. Question wants us to calculate the estimated number of hummingbirds after 10 years, rounded to the nearest whole number. Okay, so let's do that. What I want to calculate is S10, and it will be L to the power of 10 times S naught. I'm just going to plug that in my calculator and see what I get. Okay, so we've got the matrix there. I just need to raise it to the power of 10, so let's do that. Okay, and so there's our population. Now, this question asks us to round it to the nearest whole number, so let's do that. We can see that we've got 1,034 0 to 1-year-olds. We've got 796 1 to 2-year-olds, 516 2 to 3-year-olds, and finally 3 to 4-year-olds are 282. Okay, great, we did it. Okay, here's our summary slide. We looked at lots of stuff today, transition matrices, state matrix, and the Leslie matrix. I just have left the formulas there, but notice that these two and these two are very similar. They're exactly the same, it's just we've changed T for L. So L is that Leslie matrix example that we went through. All right, up next we're looking at equilibrium and steady state solutions, so stick around for that. Whoa, steady on. Today's lesson is all about balance. Welcome to the equilibrium state matrix. Today, we've just got one key knowledge point to go over. That's equilibrium state and the steady solution. So let's have a look at what that is. Okay, today's lesson is to do with the stuff that we looked at in the last lesson. So if those transition matrices aren't really making sense, then it's pretty hard to progress. So you do need to sort of sort that out a little bit. Now, it turns out when you have one of these transition matrices, that if you keep multiplying it again and again and again, that it will approach some sort of finalized state. That is, it won't keep changing randomly, but it will sort of like level off at a certain solution. Okay, so let's read the points we've got here. A state matrix, S, contains the information of a system at a point in time. So we've seen that before. So S naught, for example, was the initial population, or initial, well, actually, yeah, we've been looking at population mostly, so sort of the initial settings. Okay, an equilibrium state matrix is reached when successive iterations of Sn yield no noticeable change in the elements of Sn. Okay, so what does that mean? If you keep applying that transition, that you do another one and you actually don't see a change. You do another one, you don't actually see a change. So whenever that stops changing, that's what we call the steady state solution, or we'll think of it as reaching the equilibrium state matrix. Just generally, you might just casually say this is as reaching equilibrium. So look at this example here that we had about people moving from Melbourne to Adelaide. It turns out if you calculate T infinitely, then it'll come out as that the population at Melbourne settles at 4 million and the population at Adelaide settles at 2 million. Now, you might be looking at that and asking, well, how did you take it to an infinite power? I don't really understand that, and that's fine. I guess mathematically what we would do here is, if we're doing something advanced, we'd calculate a diagonal matrix and then take the limit of that thing as the power n goes to infinity, but that's beyond the scope of this course. How we're actually going to deal with this complexity is we're just going to take some high values of n, say maybe 30, 60, 100 should be high enough, and we're going to see when that that final matrix here sort of stops changing. Okay, so let's stick with this example. Instead of just writing S infinity, we're going to take some high values of S. So we've got this same idea about people migrating from Melbourne to Adelaide and from Adelaide to Melbourne. And what I've done is I've computed every 10th state matrix of this population. I've tabulated the results. So calculating Sn for large values of n allows us to approximate S infinity, thereby indicating the long-term trend of a scenario. So in that last slide, I actually went and did it properly and found the limit of those matrices as sort of we approach infinite calculations. But we're going to see that if we do 80, looking at 5 to 6 decimal places here, we're actually going to reach that point in 80 transitions. Okay, so what I do, I had S0, and that was 5, 1. And then I put in the transition matrix to the power of 10 times S0, and I got out this one here. And then I did S20, S30, S40, S50, S60, and S70. And you can see that this top number is approaching 4. Okay. Now, truly in the calculator's brain, it might actually be 4.000001, like something sort of with more zeros than this one. But the calculator is just set to show me up to 5 decimal places, and once there's no change, it might just actually go to one figure. So here in the calculator's brain, it might not be exactly 4 at exactly 2, but it's clear to us that these are the numbers that we're approaching. I know in the textbook it might say that you only need to do 30 to 60 transitions, but I think what you want to do is you need to keep trying the calculations in your calculator until you find that point where it stops changing. Let's look at a worked example. It says a population of Australians migrate between Melbourne and Canberra according to the transition matrix T is equal to 0.15, 0.8, 0.85, 0.2. So we've got a new transition here from Melbourne to Canberra, so we've got a different transition matrix. The population in millions of Melbourne and Canberra in 2023 are stored in the initial state matrix S0. So we've got 5 million in Melbourne and 0.3 million in Canberra. Okay, so calculate the equilibrium state matrix rounded to 2 decimal places, and part B is explain the long-term expected population of Melbourne and Canberra. Okay, so what we want to do now is we're going to pull up a calculator. Okay, so we've got our calculator here, and so I need to, I'm going to use the trick to store the matrices as a letter. The Casio can do this too, so it's not too hard. It's in the keyboard settings. So let's have a look. So I'm going to put T in as T. Let's go at a calculator. Let's put T, and we will define T. So I'm going to press Control and this button here, and that gives me the define key. So I'm going to define key to be a matrix. So I'm going to go Menu, Matrix, Create Matrix, and I want a 2 by 2. And let's put in the numbers. So I've stored that matrix. Now, if I press T and press Enter, it will give me that matrix back. So in its brain, the calculator remembers that matrix is T. Now I'm going to store S as well as S0. So let's do S and Control Define, and we'll put a matrix in. And we're going to need a 2 by 1 matrix. Okay, and we're going to store that as 5, 0.3. Okay, so now I've got T and S stored, and I want to calculate the equilibrium state matrix. So I'm just going to throw in 10 and see what happens. So let's take T to the power of 10 times S. Okay, this just keeps it simple for me to work with rather than having to draw the matrices all the time. So press Enter. Okay, so I got that matrix there. It's at 2.6, blah, 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 and 2.69, and so on. So that looks good, but I don't know yet if it's changing or not. So I'm going to go to 15, say. So T to the power of 15. And there we are. And I can see that's still shifting around, so the numbers have changed there. So I'm going to jump to 20. Okay, so in that last example, I can see that 2.57 is different from 2.56. So I'm looking for that second decimal place to remain steady because this is rounded to 2 decimal places. Okay, so I'm going to keep going until that that second decimal place stops moving. So I'm going to go back and press 25. Okay, so that would round up to 2.57. All right, I'm going to keep going. I'm going to go to 30. Okay, that one seems to be stable there. I can see that it hasn't moved from 2.56 to 2.73. And so I'm pretty confident now that that's going to be the equilibrium state matrix. So for part A, the matrix is 2.57 and 2.73. And that's in the millions of people. So over time, what this means, over 30 years of this particular transition, the population of Melbourne and Canberra will settle at 2.57 million and 2.73 million, respectively. Okay, and that's sort of what Part B means. It says, explain the long-term expected populations of Melbourne and Canberra. So the long-term expected populations will be 2.57 and 2.73 million. Okay, there you go. The long-term expected population of Melbourne and Canberra will be 2.57 and 2.73 million, respectively. Okay, so here's our summary. The main takeaway today is this idea of the equilibrium state matrix containing our steady state solution. With transition matrices, we often expect the change in population or whatever values they are to approach some figure, and that's our steady state solution. Up next, we're going to look at more applications of transition matrices, so I'll see you there. Okay, today we're inspecting insects. Today's lesson is about observing trends within a population. So we can use matrices to model different groups. And so these groups could be sort of caterpillar, cocoon, and butterfly. So let's jump in and check it out. Okay, this is applications of transition matrices, part 1. Okay, the 3 main points we're looking at today are transition diagrams and transition matrices, which we've sort of already seen. We're doing population models and insect populations. Let's check it out. Okay, transition diagrams and transition matrices. So our key takeaway here is that a transition diagram represents a flow between states. So we already saw this in that first example. So here we've got maybe 2 states or maybe 2 cities, A and B, and people or objects flowing between them. A transition matrix also represents flow between states. So a transition diagram has an associated transition matrix, and these 2 here are related. In both a transition diagram and a transition matrix, the total percentage flowing away from a point must sum to 100. In the transition matrix, this is in the column, adding to 1. So you can see both of those columns add to 1. And here from A, if we look at what's flowing out of A, here A is flowing back to itself, and that's 60%. And A flowing to B is 40%, and that equals 100%. Likewise, we can see 88% flowing out of B plus 12% flowing to A gives a total of 100% flowing from B. Okay, an example we have here is a transition diagram is useful for describing the migration of a population between 2 or more locations. And we've already seen a few examples like that. Okay, here's a pretty gnarly transition diagram, and we're going to take that diagram and encode it into the matrix. So we're going to do this one step at a time. We're going to look from W first. I'm going to fill down the column, I reckon. So if I look here from W to W, 5% flows back to W. So I'm going to put 0.05 there, just converting that percentage to a decimal. All right, now I can see that 70% of what's at W flows to X. And so I'm going to put 0.7 there. And I can see that 20% flows to Y. So I'm going to put 0.2 there. And does any flow to Z? Yes, it does. Whoop, there it is. Beautiful. So we've got 5% there flowing to Z, so 0.05. I'm just going to stop there and check that all adds up to 1. So 0.05 plus 0.05 is going to be 0.1, plus 0.2 is 0.3, plus 0.7 is 1. So, yep, that's looking pretty good. All right, I'm going to clean up the diagram before I do the rest. Okay, now I'm looking from X and where the things from X flow. I can see here X is flowing to Y, or 50% of what's at X is flowing to Y. So I'm going to put a 0.5 here. And what else can I see? I can see 0.5 or 50% of X is flowing to W. And so I can put 0.5 here. And that's everything. And I can see actually that's the only 2 arrows flowing out of X. So I'm going to put zeros everywhere else in the column. Okay, let's clean up the diagram and do Y. Okay, so looking at Y, what's flowing out of Y? Well, I can see 10% here flowing to W. And I can see 90% flowing to Z. Okay, so I'm going to put 0.1 from Y to W and 0.9 from Y to Z. Remember, with these transition diagrams, we read them column first, and that's sort of weird and different to all the other stuff we do with matrices. So chuck some zeros in there. That's all good. Last one. Okay, last one. What's flowing out of Z? I can see Z has 25% of whatever's there flowing back to Z. So I'm going to put a 0.25 down here. And I can see 75% flowing to W. So I'll put a 0.75 just there and zeros everywhere else. Okay, and that's our transition matrix from that transition diagram. Okay, population models. The key takeaway here is that transition matrices can be used to model changes in a population and migration within a population. Iterations of populations can be modeled using a recurrence relation. So we already saw these formulas in an earlier lesson, and so we can apply them to a transition matrix here. So here's an example. We've got a population of Australia migrates between Melbourne, Sydney, and Canberra. So this time around, I've got people moving between 3 cities. And if I'm going to model that, I need a 3x3 matrix. Makes sense. Okay, we've got a transition diagram here. Cool, we've got some numbers there. And that's been encoded into this transition matrix. So you could look there and verify that all the columns are adding to 100%, and everything coming out of each vertex is adding to 100%. Yep, so again, notice that 100% of the populations of Melbourne, Sydney, and Canberra are accounted for in the diagram and the matrix. Okay, let's look at insect populations. Our key takeaway today is that transition matrices can be used to model the population change of insects. By analyzing the evolving state matrix, the change of parts of the population can be observed. So in a lot of cases with insects, there's going to be like 3 main stages of their life, with an egg, a juvenile, and an adult. So the example I've used today is with a bee, and the bee has an egg stage, a larva stage, which I'm going to call the juvenile stage, and an adult stage. Okay, so a bee will exist as an egg, a larva, and an adult in its lifespan. This matrix stores the rate of offspring from an adult bee population, as well as the survival rate of the egg and larval stages. So this is sort of like the Leslie matrix. What we can see here is that we expect 10 offspring for every bee in the adult phase, but the juveniles and the egg phase can't breed yet. And that sort of makes sense, doesn't it? Because we know that only the bees are the ones that can make eggs, or really only the queen. But this is a model, so that's okay. So we've also got this 0.2 and 0.7. Okay, and they're telling me the survival rates of the eggs and the juveniles. There's no survival rate for the adult bees, and so what that means is we expect all the adults to die in the next year. Okay, so what we've got here is I've got this population of bees, and I'm calculating the population over a series of years. So here, that's the initial population. We start with 100 eggs, 100 juveniles, and 300 adults. And after several years of this transition matrix, we can see that we've got a new population here. We've got over 1,000 eggs, over 1,000 juveniles, but only 27 adults. Okay, there's our summary. There's nothing really too new in there. Maybe the eggs, juvenile, adult thing is slightly different to the Leslie matrix, but I think we'd seen those transition matrices before. So make sure you can convert a transition matrix to a transition diagram and vice versa. Okay, up next is applications of transition matrices part 2, and that's the last one for chapter 7. So I'll see you there. All right, welcome to the last lesson of chapter 7 on matrices. Congratulations, you made it. This last topic is about culling and restocking. So it's not a very happy topic. I've left an article there if you'd like to read more about culling, and the article's title is Why It Divides Australia. And I guess it does. Some people think that we shouldn't cull, and I think there are some arguments as to why we should. Maybe have a read and see what you think, and maybe talk to your peers about it. Okay, applications of transition matrices part 2. Let's do it. Okay, in this lesson, we're going to look at culling, we're going to look at restocking, which is just a slight variation on the transition matrix stuff we've done before. First up, we've got culling. Culling is the reduction of an animal population by slaughter. Culling will reduce the population from one state to the next. The population of a species can be modeled by the following recurrence relation. What I want you to notice here is that this is almost the exact same equation as what we've used before. All that's new is this matrix B. And that matrix B will have the same order as S0, so the initial matrix. And that's because it just adds on to those relevant sections of the population. So here, in this example, I've got a population of kangaroos is spread over the council areas of Banyule, Nillumbik, Whittlesea, and Darebin. Okay, and I intend for them to be, I think, in this order there. And what I'm saying here is that this here is S0. They're the initial populations of Banyule, Nillumbik, Whittlesea, and Darebin, respectively. Okay, so the only new matrix here is so we could calculate some matrix and we take a proportion of those. So the kangaroos are sort of moving between those different areas, those council areas. But here, after we work out that transition, we remove a section of the population. So that would mean that we remove 20 kangaroos from Banyule, we remove 10 kangaroos from Nillumbik, 30 from Whittlesea, and 40 from Darebin. And every time we calculate a new state, we remove those again. So we could think about doing this every month, and that's the example that we've got here. Okay, so it looks like if we calculate the populations after 1 month, then kangaroos from Banyule, there's been 1,000, and we've left with 530 after they've moved around, and we've removed some. In Nillumbik, we've got 140 left. In Whittlesea, we've got 830 left, and in Darebin, we've got 2,500, so more than we started with. Okay, if you kept doing this, or if you added those numbers up, you notice we have less kangaroos in this column than we do in this one, and that's because we're removing some of them, but we're not increasing any from the transition. So the transition just serves to shuffle them around, and the culling removes them from that whole population. Okay, so here's a worked example. We've got a population of kangaroos is spread over the council areas of Banyule, Nillumbik, Whittlesea, and Darebin. So looks like we've got the same matrix here and the same initial starting point. And we worked out S1 on the last slide, which was there. And this time we're being asked to find S2. So we're going to use our matrix to do that. So let's jump in and do it. Okay, so I've put the matrices in the calculator. Notice we've got the transition matrix and the culling matrix in there. And that culling matrix has all negative values in it. You wouldn't have to do that. You could actually put a minus instead of a plus outside. So long as whatever you're doing makes sense is fine. Anyway, so this should give us S2. Oh, wait, no, it shouldn't because I've got S0 in here. That's okay, let's just fix it. Okay, there we go. So I've got the transition matrix times S1, and then adding the culling matrix gives me S2, which is 417 in Banyule, 69.5, so that'd be 70 in Nillumbik, and then 300 Whittlesea and 3,113 in Darebin. So there we go. Let's write it down. I haven't been asked around here, so I'm not going to, because this is just a model of the population. I know that I can't have half a kangaroo, so we're just sort of predicting around this number. Okay, on to restocking. And this is the opposite of culling. Instead of removing things after we've done that transition matrix, we're going to add things into the population. So here we've got, this could refer to livestock. So you're sort of purchasing more cows or more sheep or something for your farm. Or, you run a supermarket and things move around the shelves and then you're adding them in as your stock's coming in or something like that. So we've got an example here. Notice that the matrix is the same. It's just this time B will have positive values in it because we're adding numbers to that resulting matrix. So our example says a farmer moves his cows around his paddocks, of which it looks like he has 3 paddocks because it's a 3 by 3 matrix. He does this in order to feed and medicate them. He also decides to expand his business by purchasing more cows every month. So that there tells me that this transition is occurring every month. The associated transition matrix, initial state matrix, and restocking matrix are T, S0, and B. Cool. So we've got those things there. And if we want to calculate S1, then we need to use this formula, which is just this one here in the purple box. So let's do that. We've got S1 will be equal to T times S0 plus B. Okay, so subbing all those in, S1 will be the transition matrix times the initial state matrix plus this restocking matrix. And if you work that out, it's going to give you this answer here. So it looks like after we move the animals around and we add some in, we're left with 165 in paddock A, 260 in paddock B, and 1,995 in paddock C. I'd just like to point out here at this stage, in the past we've had formulas to get the nth term. So if I wanted to do like the 60th shift around or the 60th restocking, I've actually got to do that recursively 60 times. So there's no way to shortcut that particular strategy. Okay, so here's our summary. We've got some definitions of culling and restocking. and that formula just here that's slightly different from what we've seen before. That's it for chapter 7. I'll see you next time in chapter 8. Thanks.